And now everything,
and now
right?
I see it full screen. Yes.
Perfect. Okay. So let me start.
So you can start when you want. Yes, please. Do you want? I might like to make a short introduction.
Go ahead,
to our
please do.
students. So today we have the pleasure of having here with us Professor Bhiksha. He is a professor at Carnegie Mellon University. He has done extensive work through the years, both in speech, particularly robust speech recognition, and also audio processing. He has also very interesting work in privacy preserving in the audio and speech processing space. And he will be here explaining the first talk about neural networks. So please, when you can start, Bhiksha.
Okay, thank you, everyone. And thanks for being there. I don't know how many of you are here. I'm trying to figure out how to make Zoom show the list of attendees, and that currently is not showing me anything.
I'm seeing 106 people.
Okay, fine. So let me start. This is going to be a longish tutorial, 3.5 hours, and we will do it in 3 parts. We're going to go through 3 parts. First, we will talk about the historic perspective, give you a historic perspective on neural networks. The second part will deal with what they can model. And the third part is going to deal with what they actually learn. I'm not going to get into the details of learning. I'm not going to get into the details of the mathematics. If you're here expecting to see Greek and Latin, you won't see Greek and you won't see Latin. I will have a 10-minute break between each of these 3 sections, primarily because I need a break. Speaking continuously for 3 hours can be very tiresome, but also you will need a break because you can suffer from information overflow. The format of the lecture is nominally interactive, which means that I not only permit, but I also encourage interruptions and questions. That's in theory. In practice, most of you are often too shy to ask questions. Don't be shy, okay? So let me start by introducing myself. That's me to the right. I am a professor. That's what I look like in real life. I'm a professor in the Language Technologies Institute at Carnegie Mellon University. I have other affiliations. Yes, so that someone raised a hand. I don't hear a question. Okay, so let me continue. So I also have affiliations in the Machine Learning Department, the Electrical and Computer Engineering Department, and Music Tech. If you want to get in touch with me, the email ID is bhiksha@cs.cmu.edu. That's just my first name at CS. You can also use my first name at Gmail, and that also gets to me. So let's continue with the talk. First, what is a neural network? Now, before we plunge into what a neural network is, let's look at why we're even talking about this subject. Till maybe 5 or 6 years ago, nobody was really all that keenly, very few people were all that keenly interested in neural networks. And then something amazing happened. Suddenly they became one of the major thrust areas in all kinds of pattern recognition and prediction problems, where they're established state of the art at levels that simply exceeded what was achievable only 5 years ago by huge margins. Research that had been ongoing for 50 years was exceeded by a gigantic margin over a period of just a few months in some cases. So here's one, speech recognition. We've been trying to build automatic speech recognition systems since the 50s. And as late as, say, 2015, if you had used a standard speech recognition system like Siri, very often the responses you got were laughable. These things were used more jocularly than in serious business. And then something amazing happened in 2016. Microsoft published its first paper, this first report, where they said Microsoft AI beats humans at speech recognition. Now, this was on one standard task where they compared the performance of their automatic speech recognition system to what humans achieved on the same task. And they finally managed to get an error rate that was lower than humans for that task. But things have become so much better since that on a majority of standard tasks, the automatic speech recognition systems completely outperform humans. And all of this was only achievable because we switched to working with neural networks from prior methods. Same thing with machine translation. In October 2016, if you had typed in some text into Google Translate in English, translated it from English to Spanish, and then taken that Spanish, put it back in, and translated it back from Spanish to English, what went in and what came out would not have looked anything similar. In fact, they would have been completely absurd. So the difference would have been absurd. And then in 2016 November, suddenly, overnight, Google Translate began doing a remarkably good job, something that could pass for almost human. And what happened? We just switched to working with neural network machine translation systems. And the performance these days is so much better than 4 years ago. And these are gains that have been achieved in just sometimes in months that could not be achieved in the previous 30 years of research. Here's something, image segmentation and recognition. This is a very complex scene. And I got this picture off the web, but I believe this is true. This is a standard YOLO style network that not only segments out all the significant objects in the scene, it also recognizes them. So it's able to, for this person in the front, for instance, is able to recognize the bicycle, the bag she's carrying, and the person herself. All of these in just one picture. And this was not achievable just a couple of years ago. People couldn't even dream of this level of performance. Games. Ever since the 50s, we've used games like chess and Go as some kind of a standard for human intelligence. For a very long time, people thought computers couldn't really beat humans at chess. And then in the 90s, we had CMU's Deep Thought, which then went on to become IBM's Deep Blue, which beat grandmasters and finally the world champion. And since about 1995, no human being has been able to beat computers at chess. But Go was considered much, much tougher because Go has something like 10 raised to 16 more states than chess. And so it was always assumed that computers would never beat humans at Go, till AlphaGo came along. And this was just 3 years ago. And suddenly, AlphaGo, there was a famous tournament where AlphaGo beat Lee Sedol, the human champion. And these days, AlphaGo is thoroughly walloped by the latest automatic systems, which can begin learning to play from scratch. And within a matter of few hours, beat a system like AlphaGo consistently. That's how good they have gotten. And that's because they're using neural networks. Image captioning. Here's another problem. All of these pictures, this is actually a very old result. And yet, the results are remarkable. So here is a picture. Man in black shirt is playing a guitar. That caption has been assigned and typed out in English entirely by a neural network. Construction worker in orange safety vest is working on road. Well, he's not working on a road, but it got almost all of it right. Our boy is doing backflip on wakeboard. I don't know if he's doing it on a wakeboard, but he's definitely doing a backflip. Girl in pink dress is jumping in air. All of these captions have been written by a neural network which just saw the picture. It's automatic. And again, this is a phenomenal thing for a computer to be doing, writing out very intelligent captions, and we need a neural network for this. So neural networks have begun to achieve these levels of astonishing performance in a variety of tasks, like image analysis, natural language processing, speech processing, even predicting stock markets. And so as a result, we've gotten to this state in life where knowing about neural networks is no longer just a brownie point on your resume, it's a requirement. If you're working in tech, and if you're not familiar with neural networks, if you don't know what they are, if you don't know how to use them, how to build them, you won't find a job. So at least not in any field related to AI. So it's become a necessity. Now, so we sort of laid this background for neural networks being remarkable machines, and at this point, even an essential skill, knowledge of neural networks being an essential skill for people. But what are these networks? In each case, you have The network is just a box which takes in some input and produces an output. So it could take in a voice signal, it could output a transcription. It could take in an image, it produces a text caption. In the case of AlphaGo, it takes in the current game state and then suggests the next move. So we have this box in the middle, which takes in some input and produces some output. But then what's in the box? Now, all of these tasks, recognizing speech, captioning images, playing games, these are all fundamentally human actions. All of those tasks, they're actually powered by the human brain. So to begin to understand how one can build a machine that does these beautiful tasks, perhaps we should begin by looking at the brain itself. Or even before looking at the brain, at the process of cognition. What does it mean to think? Because again, all of the tasks that you saw, there's a fundamental aspect to it when human beings perform them, which is thinking. So what does it mean to have cognition? What does it mean to think? Now, people have been worrying about cognition for a very long time. Humans can do all kinds of amazing things by thought. We can learn. Our human cognition can solve problems. We can recognize patterns. More importantly, we can create new things. And most interestingly of all, we can just cogitate. You're just having a shower. For no reason at all, you're sitting there and you're thinking math and coming up with maybe a theorem. There's no purpose to it. We just, there's this complete purposeless thinking, this cogitation, which humans do, which actually leads us to perform all of these magical tasks. So all of the fact that we can do all of these means that there's something about our cognitive process that's worthy of emulation. And people have often wondered for a very long time, how do we do these? The problem is, it's not easy to understand. As Marvin Minsky says, if the brain was simple enough to be understood, it would be too simple to understand it. Nevertheless, people haven't stopped trying. The first attempts at trying to understand the human cognitive process goes back to 400 BC, or even earlier. The first person to have written about it was Plato in 400 BC. And Plato's theory back then was that the human brain cognition operates entirely through association. It's a formalism called associationism that was followed, that was believed in for the next 2,300 years. It's pretty amazing. So you had people like Plato back in 400 BC, David Hume in the 1600s, Ivan Pavlov in the early 1900s. All of these people going down all the way even to the early 1900s, people believed that the human brain operated through association. So what is association? What is associationism? The basic idea here is that we make associations between percepts that we see together. So for example, every time you see lightning, you hear thunder. So you begin associating thunder with lightning. At some point later, if you see a bolt of lightning, you're going to expect thunder. If you hear thunder, even if you haven't seen the lightning, you will believe that a lightning must just have struck, because you have formed the association between lightning and thunder. And the fact of the matter is, this kind of associationism explains a lot of even the latest models. The magic is not so much in the fact that we form associations. What was not even investigated early on and what was not understood for a very long time is, how do we form these associations and where do we store them? Sure, you associate lightning with thunder, but where is that association stored? Now, in the mid-1800s, people suddenly realized that microscopes had become very powerful, and people realized that the human brain, which is where all of this information is stored, and the human brain is basically a mass of interconnected neurons. In spite of this, it wasn't really clear, how this stores information. All we knew is that the brain has millions and millions, actually billions of neurons. Each neuron connects out to many neurons. Each neuron is connected into by many neurons. So enter Alex Bain in 1873. he came up with the first theory for how the brain stores percepts. Alex Bain was a philosopher. In those days, if you were a scientist, you did everything. You did math, you did physics, you did biology, you did psychology, whatever. And so Alex Bain was one of those classical scientists. He wrote this wonderful book called Mind and Body in 1873. And believe it or not, the first artificial neural network model dates back to 1873. The model is 150 years old. So Bain came up with the idea that the manner in which the brain stores information is through the connections between the neurons. That using the same neurons, if you connected them in different ways, it would store different information. Moreover, you can actually have these connections where the response would depend on the input. So here he even drew some examples. Here, for instance, is a network of 6 neurons. It has 3 outputs, X, Y, and Z. But then the same network is the different outputs are going to fire depending on what pattern of inputs you get. So for example, if A and B are high, X will fire. If A and C are high, Z will fire. If B and C are high, Y will fire. So although it's a single circuit, different combinations of inputs will produce different outputs. Now this seems such a normal, obvious thing to us these days. In the 1800s, this was heresy. People just thought the whole thing was implausible. But then Bain came up with even more detailed models. He showed how you can have a network where the output would depend on the level of the input. Here, for example, if the input is high, then both X and Y will fire. But if the input is not high, Y, which gets 3 copies of the input, will fire, but X, which gets only 2 copies, will not fire. So you can actually have a network which produces different outputs based on the level of the input. Again, this was heresy back in the 1800s. People didn't actually believe this was plausible. Bain also came up with a model for how the brain could learn to store these percepts. He said when 2 impressions concur or closely succeed one another, the nerve currents find some bridge or place of continuity, better or worse, according to the abundance of nerve matter available for the transition. Basically, he said that nerves that fire together, wire together. This predicted Hebbian learning 50 years before Donald Hebb. And of course, he continued to be questioned. So here's the famous statement by Bertrand Russell: the fundamental cause of the trouble is that in the modern world, the stupid are cocksure, while the intelligent are full of doubt. So in 1873, Bain postulated that there must be 1 million neurons and about 5 billion connections to acquire 200,000 percepts. Then by and by, he realized that 200,000 is a really small number for the number of percepts that a human being carries. Also, we don't always have fully formed percepts. There are all kinds of partially formed associations. And so if you begin accounting for all of those, there's no way 1 million neurons and 5 billion connections can store all of those. So eventually, by the end of his life in 1903, he figured that he was wrong. He just agreed with all of his critics and recanted his ideas and apologized so much for having these ideas. He said it's too complex, the brain will need too many neurons and too many connections for this to work. He was wrong in thinking he was wrong. A brain is much larger than he thought. The human brain has 80 billion neurons. It has 1,000 trillion connections. There's more than enough material matter there to store everything we ever encounter in life and more. And so, fortunately, Bain's connectionist theory of machines has stayed, and we all recognize now that the human brain is a connectionist machine. Neurons connect to one another, and the processing capacity of the brain lies in the manner in which these things connect to one another. And so artificial networks are basically connectionist machines which emulate this connectionist structure of the human brain. So here's what a connectionist machine looks like. It's a network of processing elements which are all connected to one another somehow. And all world knowledge is stored in all of the elements are indistinguishable from one another. The knowledge is stored not in the elements, but in the manner in which they connect to one another. This is what a connectionist machine is, and this is the model that we employ for artificial neural networks today. Now, this differs from your standard computer. Your standard computer is not a connectionist machine. Your standard computer actually is uses what is called a von Neumann or a Harvard architecture. In these architectures, you have a processor, and the memory is separate from the processor. In the von Neumann architecture, the memory is partitioned into portions that store programs and portions that store data. In the Harvard architecture, they're all the same. It doesn't matter for our purposes. What matters is that the processor is isolated from the memory. You can make the same machine perform different things simply by changing what's in memory. You change the program, the machine does something different. In a connectionist machine, that's not the case. In a connectionist machine, the machine itself is the program, because the program lies in the connections between the units, which means if you want a machine to perform a different program, you're going to require an entirely different machine, which is why even today, when we actually use connectionist networks, we don't actually build connectionist networks directly. We emulate them on von Neumann machines, because von Neumann machines are so much more flexible than connectionist machines, although connectionist machines are so much more powerful than von Neumann machines. And so, to recap everything we've seen so far, neural network-based AI has taken over most AI tasks. Neural networks originally began as computational models of the brain, or more generally, as models of cognition. The earliest model of cognition was associationism. More recent models of the brain are connectionist, where we say neurons connect to neurons, and the workings of the brain are encoded in these connections. So modern neural network models are connectionist machines. Questions, anyone? If you have questions, just raise your hand. Okay. I'm going to, all right. If none, let me continue. Give me a second. I've run out of charge.
Yeah, sorry, so someone raised his hand.
Yeah, go ahead.
Ivan de Prado, so.
Ivan, what's the question?
So I guess you can.
Hello, can you hear me?
Yeah.
Yeah, sure.
Yeah. Well, my question is just regarding the microphone. Do you have a different microphone or something? Because the sound is not so good. I'm just asking just in case. That's all.
I have two raised hands. One is Ivan, the other is Carol. What is the question, Carol? I can't hear the question, so.
Sorry, I will repeat. Can you hear me?
I can hear you. Yeah.
Yeah. So I was wondering if you have a different microphone.
My microphone? Okay.
Yeah.
So let me try.
It's kind of.
Thank you.
Hello?
Yeah?
Hi.
Can you hear me?
Much better, much better.
It's
Okay.
better, yeah.
Fine. So I think that my Bluetooth microphone was kind of broken, right?
Okay.
It's much better now.
Okay. So my apologies. And I tested it today, but then, these things sort of.
Yeah. So actually I have a question, if I may ask. So which are the limitations of following the model of the brain? Because we also see the brain is imperfect, so we sometimes get a lot of cognitive bias, and yeah, there might be a risk that also the neural networks get the limitation that we have in our brains.
So the point is, we are not mimicking the brain in its entirety, right? Eventually, all of your biases and such like are going to be dependent on the program that is encoded by the network. And we have a great deal of flexibility in the program itself. So we are not exactly replicating the brain. We are inspired by the structure of the brain, but eventually the programs we learn are very much of our own creation. So the risk of bias doesn't come from the fact that we are emulating the brain. The risk of bias comes from elsewhere. How do we construct our programs and how do we learn them? It's a different source.
Okay. Thank you.
Okay, let me continue, right? Okay. So here's where we are. Connectionist machines are networks of processing elements. All world knowledge is stored in the connections between the elements. But then the key piece of these elements are these units. The design here, the simplicity of this, the beauty of the whole structure lies in its symmetry. Every unit is exactly the same as every other unit. If you pulled out two units and swapped the two, then the machine would continue to operate exactly the same, because the information is not in the units, the information is in the connections. So what are these magical units that enable us to build these amazing and yet very simple machines? For that, we go back to the brain again. Turns out our brains are fairly magical. So the basic unit in our brain is a neuron. A neuron is a structure like this that I have in the figure here. It consists of a head called the soma. You have all of these little tendrils coming out of the head, which are called dendrites, through which other neurons connect to the neuron. If the total signal from all of these neurons exceeds some threshold, the neuron will fire. That signal goes down this long arm called the axon. And from the end of the axon, it goes to other neurons. The axon itself is protected by this little sheath called the myelin sheath. And that myelin sheath, it turns out, is made of fat. And here is an amazing little fact. If you got rid of this fat, the neuron would die and you'd lose the neuron. This is in fact a disease, right? So it turns out that your brain is largely just fat. The majority of the mass of the brain is the fat that protects the neurons. And more importantly, how smart you are is kind of a function of how much fat you have in your head. So they stored Einstein's brain, and then they analyzed it. They found he had about the same number of neurons as everybody else. What he had was a lot more fat. So it turns out being called a fat head is a compliment. It means if you're a fat head, you're really smart. Anyway, going on with it, we're going to just try to emulate this simple structure. And the first computational model for the structure was produced by these two guys, McCullough and Pitts. Now, Warren McCullough was a neurophysician in the University of Chicago, very well known. And Walter Pitts was a homeless guy who wanted to be a logician, who used to write letters to people like Bertrand Russell. And then one day when he was about 16 or 17 years old, he just wandered into McCullough's home. And so McCullough, the guy to the right, and Pitts, who looks a lot more reputable in this picture than McCullough, is the guy to the left, they got together and wrote this amazing paper on a logical calculus for the ideas immanent in nervous activity, where they came up with a model for the neuron, a mathematical model for the neuron. The basic I model was just simple threshold logic. It's not quite the figure that I have over here, but their idea for the neuron was that each neuron received a certain number of inputs, and if the total input exceeded a threshold, the neuron would fire, unless you had these things called inhibitory inputs. If an inhibitory input was ever on, the neuron could never fire. Now, the Pitts came up with a lot of extremely complicated math to explain all of this. And I don't think there's anybody since 1943 until today who has completely understood all the fine detail of Pitts' model. But here is the general concept behind their model. It's a synaptic model. Every neuron has excitatory and inhibitory synapses. Excitatory synapses transmit weighted inputs to the neuron. Inhibitory synapses have this property that any signal from an inhibitory synapse forces the output to 0 regardless of what else is coming in to the neuron. So using this, they showed that you can model all kinds of Boolean gates. This figure to the left, for instance, the neuron is going to fire, neuron 2 will fire if it receives 2 inputs. So anytime neuron 1 becomes 1 unit of time later, because it's connected by 2 connections to 2, 2 will receive 2 inputs and it will fire. So this figure to the left is just a delay, the time taken for the signal to travel from 1 to 2. The figure to the right, again, this neuron will fire if it receives 2 inputs, which means that if either 1 or 2 fire, then 3 is guaranteed to obtain at least 2 inputs and it will fire. So the figure to the top right is 1 or 2. The figure to the top left, bottom left, both 1 and 2 only have a single connection to 3. 3 will only fire if it receives 2 inputs. So both 1 and 2 have to fire for this neuron to fire. So this is 1 and 2. The figure to the bottom right, 1 connects with 2 connections to 3, but 2 has an inhibitory connection to 3. So the neuron 3 will only fire if 1 takes the value 1 and if 2 takes the value 0. Because if 2 becomes 1, then it's not going to fire. 2 is inhibitory. So this is 1 and not 2. So you see, you can construct, once you can construct all of these basic Boolean gates, you can construct all kinds of Boolean circuits. And so it eventually becomes possible to compose pretty much any Boolean circuit using McCullough and Pitts neurons. But then McCullough and Pitts overstated their case. They claimed their machine could emulate a Turing machine. You can show that it cannot because it's finite state. And they claim, and also they said we can build a machine using these neurons. They didn't show you how to build a machine for any generic Boolean function. So they didn't give you a learning mechanism. For that, we had to wait for Donald Hebb in 1949. He came up with a learning mechanism which said neurons that fire together, wire together. So the basic idea that he had was this one. Here is a typical synaptic connection between 2 neurons. The upper neuron has a head. It lies on top of the synapse, the dendrite of the lower neuron. And anytime a signal comes into the upper neuron, some chemicals are released by this head, which causes the lower neuron to get excited. Now, the larger the head, the more the chemical flow, and the greater the excitation of the lower neuron. So basically, the strength of the connection depends on the size of the head. And so Hebb said, if neuron Xi, the upper neuron, repeatedly triggers the lower neuron, then this synaptic knob gets larger. Anytime both of them simultaneously fire, the knob gets larger and the connection gets stronger. So if you assign a weight to the connection, the mathematical model for the weight is W equals W plus eta xy. Eta is a learning rate. And observe that each time both X and Y take the value 1, that is only when both the input and the output take the value 1, the weight gets incremented. This is called the Hebbian learning rule. It's still used a lot. And this was sort of assumed to be the learning mechanism till someone realized there's something broken about this, which is this, that the weights always only increase. There's no mechanism for the weights to decrease, which means that if you start with a brain and then you keep firing and you keep exciting it, you know, there will be all kinds of random associations. And each time a random association is made, the corresponding weight is going to increase and eventually all the weights will max out. And the machine is going to end up not representing anything useful. This is a very unstable learning algorithm because the only thing weights can do is to increase. So to come up with a better model, we needed this guy, Frank Rosenblatt. Frank Rosenblatt was a psychologist, a logician, and a brilliant guy. Who invented the perceptron in 1958. So this model here is Rosenblatt's, is a simplification really, but it's the one that we use of Rosenblatt's perceptron. The perceptron is a unit which receives a weighted number of inputs. It computes a weighted sum of these inputs. And if the weighted sum of the inputs exceeds a threshold, it's going to fire. If it doesn't exceed the threshold, the output is going to be 0. So this is what is commonly known as threshold logic. And it's actually a very, very nice piece of, very, very nice design for the unit. Quite brilliant. And it's so good that we still use it many, many years later. And I don't think we quite understand how to build neural networks without units like these. The problem was Rosenblatt, who was a hyper-optimist, kind of overstated it. So he assumed that this little unit could represent any Boolean circuit and perform any logic. And so you had articles like these which said, you know, the embryo of an electronic computer that the Navy expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. This was the New York Times in 1958. Frankenstein monster designed by Navy that thinks, Tulsa, Oklahoma Times, 1958. You're not speaking of a neural network. You're speaking of just this one unit. Somehow the Navy that funded this work imagined that this one unit could do anything at all and solve all of the world's problems, which of course turned out to be a flawed hypothesis. So Rosenblatt not only came up with a design for the unit, he also came up with a learning algorithm. And his learning algorithm looks a whole lot like Hebb's learning algorithm with one minor difference. Now the Hebbian rule, anytime both the input and the output were the same, the weight got incremented. Here, Rosenblatt changed it a little bit. He incremented the weight in if a neuron is already doing something right, there is no need for you to be updating its weight. This is something that Hebb ignored, forgot. So Rosenblatt said you only update the weights of a neuron when it makes mistakes. How much do you update the weight by? You update it by enough such that it will correct this mistake. So the update rule said you increment the weight by a term which is proportional to the error, the difference between the desired output of the neuron and the actual output of the neuron times the current input. So this ensures that it responds properly to the current input, but the weight itself only changes if the neuron is making an error, otherwise it doesn't. And Rosenblatt actually proved that this algorithm is a nice algorithm which converges to the correct solution under certain conditions, which we will see later in the lecture. So Rosenblatt showed that the simple perceptron can model any Boolean function. Here, for example, here are some examples. In each example, the weight of a connection is the number shown above the edge. The threshold is the number inside the circle. So the figure to the top left, X comes in with a weight 1, Y comes in with a weight 1. The neuron is going to look at 1 times X plus 1 times Y. If that sum equals 2, it's going to fire, otherwise it's not going to fire. So clearly the neuron to the left will only fire when both X and Y are 1. If either one of them is 0, the total input coming in is going to be less than 2, so it won't fire. So the neuron here is X and Y. The neuron to the bottom has a threshold of 1. So if either X or Y take the value 1, it's going to fire. So this is X or Y. The neuron to the top right, the weight is -1. The threshold is 0. So if X is 1, the total signal coming in is -1, which is less than 0, and the neuron won't fire. If X is 0, the total signal coming in is 0, which does match the threshold, and the neuron will fire. So this basically inverts the input. This is not X. So Rosenblatt's perceptron can mimic any Boolean gate, but to puncture Rosenblatt's balloon in 1968, Minsky and Papert showed that it provably cannot model an XOR function. In other words, it's not universal. That one gate cannot model every single Boolean function on the planet. So basically what we have is individual elements, the perceptrons. While they are very powerful computational elements, they are not powerful enough. They are actually weak computational elements. But then to make them actually do what you want them to do, you have to begin networking them. And Minsky and Papert showed that although individual perceptrons are not sufficiently powerful by themselves, once you begin networking them, they become much more powerful. So going back to the XOR problem, instead of using just a single perceptron, if you used a network of 3 perceptrons connected in the manner that we have over here, that will give you an XOR. The first neuron on top computes X or Y. The first neuron at the bottom computes not X or not Y. And then this final neuron out here ANDs the outputs of both of these first level neurons. And so that naturally actually gives you X XOR Y. Now, in the structure, you don't no longer just have one perceptron, you have a network of perceptrons. There's a very distinct structure to it. The outputs of the perceptrons in the middle, these two guys, which I'm showing with my pointer, their outputs are never really observed. What you only observe is the output of this final neuron. So these were what we call neurons in the hidden layer. They are hidden neurons. And the actual neuron that produces the output is the output neuron. And this structure, this networked structure which computes an XOR, was also proposed by Minsky and Papert, who showed that while individual perceptrons may be weak elements, once you begin networking them, you can compute XORs. You can compute any Boolean function. So for example, you can begin composing them to construct this ugly function over here, which is A and not X and Z, or A and not Y and X and Y, or not X and Z. I mean, it's an ugly function of 4 variables, but then you can compose it using perceptrons. You can compose any Boolean function using perceptrons. So to summarize the story so far, neural networks began as computational models of the brain. Neural network models are connectionist models, which comprise networks of neural units. The McCullough and Pitts model uses models neurons as Boolean threshold units, and models the brain as performing propositional logic, but gave us no learning rule. Hebb's learning rule gave us neurons that wire together, but it's unstable. And Rosenblatt's perceptron, which is a variant of the McCullough and Pitts neuron using a variant of Hebb's rule, which gave us a provably convergent learning rule, actually gives you a more powerful learning perceptron than the previous ones, but the individual perceptrons are limited in their capacity. Once you begin networking these perceptrons, however, a structure that we call a multi-layer perceptron, it can model arbitrarily complex Boolean functions. So that's great. So we know that the neural network can model pretty much any Boolean function. But then, we said this was a model for the brain, and the brain is not a Boolean machine. We don't work on Boolean inputs. Look at the world around you. They are not Boolean. It's continuous value. We have real inputs. We make non-Boolean inferences and predictions. And so let's go back and look at the perceptron and see how it behaves for real valued inputs. So in this case now, x1 through xn, the inputs would be real valued. The perceptron is going to see a weighted sum of all of these real valued inputs. If the weighted sum exceeds a threshold, it's going to fire. Otherwise, it's not going to fire. So that is the equivalent of saying I'm passing this weighted sum through a threshold function, which produces a 1 if the output is greater than some value and 0 otherwise. You can soften that and say, instead of having a threshold function, I can have a smooth function whose output goes from 0 to 1 as a function of the input, like so, in which case you can view the output as a probability of firing. But for the purpose of this lecture and part of the second part of this lecture, I'll continue to assume that the unit is the final function applied to the weighted sum of the inputs is a threshold. There's a threshold function. So here is the perceptron. Now, how exactly does this perceptron operate? it produces a 1 if the weighted sum of inputs is greater than the threshold. It produces a 0 if the weighted sum of the inputs is less than the threshold. What is the boundary between the two? The boundary between the two is when the weighted sum of the inputs is exactly equal to the threshold. So summation wi xi equals t. That is the equation for a hyperplane. In 2 dimensions, that's going to be the equation for a line. And so this line separates the region of the input space where the neuron would produce output a 0 from the region where the neuron would output a 1. And if I were to actually plot this in 3 dimensions for 2-dimensional input, here is this line here is the same one shown at the bottom here. And when the input lies on this side of the line, the output is a 0. And once you just go to the other side of the line, the output jumps up and it becomes a 1. So this perceptron over here actually models this threshold function. So now, when the perceptron operates on real input, it computes threshold functions. How do you explain the behavior for Boolean inputs? It turns out it perfectly explains the behavior for Boolean inputs. When the input is Boolean, the inputs are either 0 or 1. So if I have 2 bits, 2 inputs, the input combinations are 0, 0, 1, 0, 1, 1, or 0, 1. The threshold is going to be this line. And the output is going to be 1 on the pink side and 0 on the white side. And you can see that in this case, whenever any of the inputs is 1, the output is a 1, otherwise it's a 0. So this is X or Y. If I simply slide the threshold over to this point that I have in the middle figure, then the perceptron only fires if both inputs are 1. So the perceptron now becomes X and Y. For the figure to the right, the neuron fires whenever Y is 0 and doesn't fire when Y is 1. So this becomes not Y, it's ignoring X. So basically what we're seeing is that a perceptron that works on real valued inputs can do Boolean functions if the inputs themselves are Boolean, and they can give you and, or, and not. Pardon me, this is, right? So this is, how do I turn this on? Give me a second. Yeah. So yeah, now when you look at this, you should be able to figure out why we cannot compose an XOR. Because if you want an XOR, you want the output to be 1 for 0, 1 and 1, 0, but you want the output to be 0 for 0, 0 and 1, 1. So you want the function to go up for this band and then go back down before going ahead. And the perceptron doesn't actually give you a function of this kind, it's just a shear step. But anyway, once you figure out that a perceptron can do something of this kind, where it's going to give you a 1 on one side of a line and 0 on the other side, you can begin composing networks to obtain much more complicated decision boundaries. Consider this pentagon. We want a network that outputs a 1 if the input is inside the pentagon and 0 outside. So here's how we will do it. I'm going to start off with a first perceptron, which produces a 0 when the input is in this white region, and a 1 when the input is in the yellow region, which basically captures the lower boundary of the pentagon. Then I will have a second perceptron over here, which similarly captures this edge of the pentagon, producing a 1 on the yellow side and a 0 on the white side. And so I will have one perceptron for each of these 5 edges. Now observe the manner in which I actually compose the perceptrons is such that all 5 of them have an output of 1 inside the pentagon. But outside the pentagon, at least one of the perceptrons is going to produce an output of 0. And so if I just sum up the outputs of all of the perceptrons, the sum is going to be 5 only inside this pentagonal region, and it's going to be less than 5 outside. And so now if I simply take all 5 inputs, add them up and compare them to a threshold of 5, basically I can, by applying a little perceptron, combining these 5 outputs by a perceptron, which compares their sum to a 5, I can produce a network which outputs 1 when the input is inside the pentagon and 0 outside. And so now I have been able to model the pentagonal decision boundary. But once you know how to compose a pentagonal decision boundary, you can actually make much more complex models. So let's say I want a network that will fire if the input is inside either of these 2 yellow regions and 0 outside. Here's how I would do it. I would have one subnet which outputs a 1 inside the first pentagon, a second subnet which outputs a 1 inside the second pentagon. Then I OR the 2 outputs and I'm going to get a 1 inside this double figure. And once I can do a boundary like this, I can have more complex decision boundaries like this one. I'll let you figure out how we would do this. We'll get back to this in an hour or so anyways. So in a standard classification problem, what exactly are we doing? In a standard classification problem, our job is to find decision boundaries in high dimensional spaces. For example, if I'm recognizing digits in the MNIST corpus, I will have a 784 pixel input. It's basically an input in a 784 dimensional space. I want to decide if the input is a 2 or not. That is the equivalent of saying that in this 784 dimensional space, there's this region, and if the input lies within the region, I want the output to be 1, otherwise I want it to be 0. Well, once I know the region, I can use the same logic that I had before to actually construct a network that captures that region, and I can build a neural network that computes this decision near perfectly. And so the story so far, multi-layer perceptrons are connectionist computational models, where individual perceptrons are computational equivalents of neurons. The MLP is a layered composition of many perceptrons. MLPs can model Boolean functions. Individual perceptrons can act as Boolean gates. Networks of perceptrons are Boolean functions. And MLPs are actually Boolean machines. When you think of real valued inputs, they represent Boolean functions over linear boundaries, and they can represent arbitrary decision boundaries, which means they can be used to classify data. Questions, anyone?
So there are 2 questions in the chat, in the Q&A. So the first one is about the von Neumann machines. So I'm still a bit confused by the discussion of von Neumann machines versus neural networks. I think I get that. Yeah. So yeah, more explanation.
Okay, so let me answer that question first. In a von Neumann machine, you have the von Neumann architecture separates a memory from the processor. The program is the content of the memory, not the memory itself, which means that I can just flip all the bits in my memory to 1s and 0s, and every time I flip them, I get different programs, right? So which is why your simple smartphone can perform so many different tasks, because all you do is you change the program in the memory, and the same processor is going to compute. If you just change the program, the same processor is going to compute a completely different program. In the neural network, I have 2 neurons. They're either connected or they're not. If they're connected, the connection is permanent, right? So in the connectionist architecture, the architecture of the processor itself is the program. The value of these connections, that is the program. So this means that if I want to change the program, I have to change the processor. I've got to change all of the connections. We don't actually build things that way for that reason, right? We actually emulate these. Does that answer the question? What was the second question?
Yeah, it's another question. So yeah, the question is, yeah, you will not only have, so when you were talking about the perceptron, they asked this question. So you will not only have different connections, but also different neurons. So then neurons. So some neurons will be active when the value is 2, and some of them will be active when the value is 1. So then the question is, then not just the connection matters, but the time of neurons also matter. So we cannot swap neurons.
I'm not sure what you mean by type of neuron. The neuron is structure is exactly the same. You're looking at the outputs of the neurons, which is very different, right? So when I have all of these things connected, it's not permanent. So if all of those outputs, anything that depending on what the neuron gets at the input, its output is going to change. So that's part of the computation.
Okay, great. So yeah, there are no more questions for now.
Okay, so let me continue, right? So finally, is there a semantic interpretation to what the network actually computes? Let's go back and take a look at the perceptron. The perceptron is computing a weighted sum of the inputs and comparing it to a threshold. But then if I think of these, the set of inputs is a vector, the set of weights is a vector. So this weighted sum is simply the inner product between the input vector, x, and the weight vector, w. And the perceptron fires if this inner product exceeds a threshold. Otherwise, it doesn't fire, right? Now, what does this mean? We know from geometry, from our algebra, that the inner product between two vectors, x transpose w, is simply going to be the magnitude of x times the magnitude of w times cos theta, where theta is the angle between the two vectors. Now, in high dimensional spaces, all vectors are pretty much the same length. I know this kind of sounds bizarre, but then it's a well-known fact that as you keep increasing the dimensionality of the space, for any sphere, nearly all of the volume lies very close to the surface of the sphere. The fraction of the volume that lies away from the surface of the sphere becomes smaller and smaller, and as the dimensions increase, that becomes infinitesimally small. So which means that if you take any two random vectors, they're basically the same length, which means that the length of x and the length of w are going to be more or less the same. So you're saying that the neuron will fire if x transpose w is greater than threshold, or assuming, without loss of generality, that the length of w is 1, this is going to fire if cos theta is greater than t over the magnitude of x, or if the angle between the input and the weight vector is less than this value over here. Again, keep in mind that the norm of x is going to be the same for all x's, so this is some kind of a constant. And so basically what we're saying is that the weight is a vector in the space, and anytime the input is close to the weight in angle, the neuron will fire, otherwise it will not fire. So you're literally saying how similar is the input to the weight. In other words, the neuron is actually just a correlation filter. So let's say I want to recognize the digit 2 on this grid. If I want to recognize the digit 2, all I would do is to create a perceptron with each cell going into the perceptron, but the weights would follow this pattern shown in black, which represent the digit 2 itself. And then if I get an input of this kind, the one in the middle, the correlation, the inner product is just the correlation between the input and the weights. Here the correlation is low, the neuron wouldn't fire. Whereas if I got something like this figure to the right, the correlation is 0.82, it's going to be higher, the neuron will fire. Basically, the perceptron evaluates the degree of correlation between the input and its pattern of weights. That's for a single perceptron. Now, when you have a more complex structure, then let's say you have a network which looks at this grid of pixels, like your old LED watches, and it outputs a 0 or 1, depending on whether it thinks this grid of pixels contains a digit or not. You would have a 2-layer network of this kind. The first layer would comprise feature detectors, which detect specific patterns in the input, like the horizontal bar or the vertical bar to the edge on the top, the vertical bar to the edge at the bottom, and so on. And then the rest of the network is simply a Boolean function over these feature detectors. So you can expect that the second level neurons now are going to be firing when certain patterns are found for these bars. So if the first neuron here might fire if all of the patterns that correspond to a 1 do fire, and the ones that don't correspond to a 1 do not fire, and so on. And so you'd expect all of these second level neurons to capture the individual digits, and the third level neuron is only going to check if any of these have fired. So basically the entire network can be viewed as a cascade of feature detectors. Now, it's not as simple as what I have over here. You can also have negative feature detectors, which is to say that if you see a particular feature, a pattern has not happened. So the general idea remains that the network is a cascade of feature detectors. Each neuron is a correlation filter, which finds out how much the input pattern matches the pattern in its weights. The network itself is a cascade of such correlation filters, of such feature detectors, where higher level neurons compose complex templates from features represented by lower level neurons. So to add that to our story, perceptrons are correlation filters. They detect patterns in the input. MLPs are Boolean formulae over patterns detected by perceptrons. So higher level perceptrons may also be viewed as feature detectors. And then finally, if you think of MLPs in classification, the network will fire if the combination of the detected basic features matches an acceptable pattern for a desired class of signal. For example, if it finds an appropriate combination of nose, eyes, eyebrow, cheese, and cheek and chin, it's going to call it a face. Now, the final bit for part 1 of these 3 lectures is we've seen neurons and multilayer perceptrons as Boolean functions. We've also seen them compute Boolean functions over real inputs, so basically to performing classification. But what about networks as real valued functions where the output itself is real valued? So can networks be continuous valued regressions? For that, let's look at the structure here. This is a simple 3-unit MLP where the final neuron doesn't perform any threshold, it simply sums the input. This first neuron over here, T1, fires if the input exceeds the threshold T1. The second neuron fires if the input exceeds the threshold T2. T1 and T2 connect to the output with weights 1 and -1. So when the input is less than both T1 and T2, both outputs are 0. The outputs of both T1 and T2 are 0, so the final output is also 0. If the input is greater than T1 but less than T2, then the first neuron is going to fire an output of 1. The second neuron is going to output a 0. So the sum of the two is going to become a 1. When the input continues to increase and the input is greater than both T1 and T2, both of these neurons will fire. And because their weights are 1 and -1 respectively, when you sum them up, they're going to cancel each other out. And so if you look at the output f of x as a function of x, until the input x arrives at T1, the output is 0. When the input is between T1 and T2, the output is 1. Beyond T2, the output becomes 0 yet again. So now we got this nice little square pulse over the input. Once you know how to do that, you can compose any arbitrary continuous valued function of a single variable. So let's say I want to build a network which composes this blue function, which is a function of a single variable. All I have to do is to have a very large number of neurons of this kind, where each pair of neurons computes one of these pulses. I can scale their outputs by the height of the blue function within this pulse. And so as a result, the summed output of all of these pairs of neurons of this large network is going to be a stepwise approximation of the blue function itself. And I can make this approximation arbitrarily precise by making these pulses arbitrarily narrow. In other words, I can approximate the blue function with the level of precision that I want, regardless of how much precision you require of me. So a neural network can model continuous valued functions. So in other words, a neural network can model pretty much anything. MLPs are connectionist computational models, which can model any Boolean function. They're classification engines that can capture any decision boundary, and they do so by detecting basic features and composing patterns from these basic features and seeing if the input matches a pattern that is acceptable for the given class. They can also model continuous variant functions. So that's the end of the first part of this lecture. I'll stop here. I'll give everybody and myself a 10-minute break. The time on my watch is 1:10. We will restart at 1:20. And I'm not going to be available for the next 10 minutes. If you have any questions, please hold on to them. I will answer them when I get back. I'll leave the screen open. Thank you.
Thank you, Bhiksha.
Mm.
Okay, let's do 10 minutes break, okay? Let's start at 6:20.
Okay, can you hear me?
Bhiksha. Yes, we can hear you. There were some questions.
Yes, okay.
I can read them. So the first one is from Evo. Are there any types of features, Boolean, continuous, categorical, that work better or worse in neural networks?
So you'll have to sort of wait for the end of this lecture. The way we've been explaining things so far, I'm using threshold activations, where you're looking for very specific kinds of features. Now, in all of these, there's no what you can model. You can model pretty much anything. The neural network is what is called a universal approximator. We'll see that in the next part of the lecture. And because it's a universal approximator, it does not matter what kind of feature it is, it can model it, so long as the neural network has the capacity to learn it. And what do we mean by having the capacity to learn the network, to model it? And what do we mean by having the capacity to model something? You should have a sufficient number of neurons connected in an appropriate manner, and then it can model it. So, and there are no restrictions, absolutely none. It is a universal approximator. You give it a function, it can model it, provided the network has the capacity to do so. And the problem really is this business of capacity, which is very poorly defined. And we can field questions on the notion of the capacity of the network at the end of part 2.
Awesome. So the next question is more of a sort of general question that I don't know, maybe we could also answer it later. It's whether it's related to the current challenges that neural networks are facing.
So what do we mean? What is the question exactly?
What are the current challenges neural networks are facing?
And what are the current challenges? Right now, I wish there was a nice closed answer to that, right? The way we go about it, we identify a pattern recognition or a prediction problem, and then we try to compose networks to learn these, to model these problems. The biggest problem that we always end up with, the most important problem that we've dealt with over the years is, how do you actually train the network? There's a difference between saying a network can model something and saying a network does model something. In other words, we saw this little model that we saw for the pentagon example. I could hand draw the model because I know exactly what it has to be like. But then if I just gave you lots and lots of examples from the pentagon, where I give you XY coordinates and whether the output is a 1 or a 0, then you're going to have to infer that it's a pentagon, figure out what the appropriate network structure for it is, and then determine the parameters of these neurons. That's much bigger than me just saying, oh, I can do it, and here, let me hand draw it, right? So the big challenges that we end up dealing with is all these levels of inference, finding out what the underlying function is and what is the best way of modeling it. And even if I give you the appropriate model structure, trying to find what these parameters are ends up becoming a huge challenge. And a lot of the work that we currently see has more to do with techniques for learning the parameters as opposed to finding the appropriate network itself. Now, it's a whole new topic that I am not covering here. But then if you have questions about it, I can deal with it over email, or if you guys have a piazza or something, I can answer.
Yes, we have a Slack channel on the lecture, so that can work for following up on that. And so the final question is, there's another one, but I'm gonna read the first one first. Okay, if the weights are indeed a correlation filter, why do we have to learn the weights? Why can't we initialize the weights based on our input?
You could try. The problem is that in most cases, for simple problems, it's easy, right? For simple problems, you wouldn't know what, but then think about really something simple like recognizing irises, right? Human irises. What is the best way to, it's known by now that, correlation filters do a fantastic job of recognizing irises, but then there's not just one kind of iris. There are hundreds of different types. then that means you're going to have to know what each one of these guys are, and then find the appropriate correlation filter for each of these and construct the final network for it. The real problem is in knowing what the constituent patterns are, right? If some oracle came and gave you all of the constituent patterns, then clearly the most sensible thing for you to do is to actually simply handcraft correlation filters for every one of these constituent patterns. The problem is we don't know. I mean, go back to the iris example. There are thousands of types of irises in the world. How do we even know what those patterns are? If I decide to hand choose some 50 of those and compose neurons for those 50 types of irises, what happens to the remaining 500,000? Now, if you want to begin clustering them and grouping them, what is the optimal way of grouping them such that your standard pattern is actually represented? All of these problems basically amount to learning the network.
Great.
Shakir, what was the question?
Yes, and there's a couple of questions more. Can we build computers using perceptrons since they can emulate logic gates?
Yep, that's the, I mean, let me put it this way. You actually built perceptual computers using perceptrons. Threshold logic is a very well-known logic. And there's a whole field of computer science in analyzing the complexity of threshold circuits and so on. And threshold circuits are a very standard component of Boolean circuitry. So to give you a very simple example, suppose you want to build a majority gate, meaning you're given Boolean inputs. We'll see that in a few minutes. But you're given Boolean inputs and you want to say, I want this network to fire, this neuron to fire if at least 10 of these inputs are on. If you want to do this with standard AND and OR gates, the size of the circuit will become exponential in the input. But with a threshold gate, it takes only one. And so we actually use threshold gates in standard computers all the time. Those are perceptrons.
Great. And then a question related to a previous one, which is, what if we initialize the weights with input data if there is correlation?
That's a brilliant idea and somebody should try it. It makes absolute sense. And I'm always surprised not to see a paper on the idea.
Actually, that makes me remember about how ResNets work, because they were just learning the residuals instead of like trying to learn the whole thing. So I think it's kind of related to that.
And you'll remember that in the past, people also confused, and I mean, one of the easy ways of learning in initializing networks was to compute principal components of inputs and use the PCA bases as weights.
Nice.
Right? And
so those.
Yeah.
Yes. Awesome. So those are all the questions for now.
There was
Thank you
one
very
more.
much.
Yeah, Shakir.
Is there?
There's one more.
Oh yeah. Oh no, that was Shakil's question was about this initialization of weights.
Okay, fine. That's it? Okay.
Yeah, that's it.
Very good. Thanks for the questions, kids. Appreciate it. Okay. It means you're listening, right? Now let's continue. The second half is the second part. Well, I have 3 halves to my lecture. And so the second half of my lecture is, what can a network represent? Here's a quick recap. This is the perceptron. It's a threshold unit. It fires if the weighted sum of inputs and the bias is positive, right? So I'm just restating it slightly. Instead of saying I'm comparing the inputs, weighted sum of inputs to a threshold, I can say I'm computing the weighted sum of inputs minus the threshold, which gives me an affine combination of the inputs. And the output is 1 if this affine combination is 0, is greater than or equal to 0, and 0 otherwise, right? So this affine combination is put through a threshold activation. You can, once you think of it that way, then you can say, instead of having passing the affine combination through a threshold activation, I look at it through a sigmoid. We will encounter the sigmoid again. The sigmoid activation replaces the threshold with a smoother version of the threshold function, which has this form 1 over 1 plus e raised to minus z. And the reason we use the smoother version is that it's differentiable, whereas a threshold function of this kind is not differentiable. The derivative is either 0 or undefined. and so not very useful for learning. Now, this is just a by the way, because we're not going to actually spend a lot of time on activations, but just to give, except maybe towards the end of part 2 of this lecture. Now, there are other kinds of activations like the tan-H, which is simply the sigmoid move down, or the rectified linear unit, where the output is the same as the input if the input is positive, 0 otherwise, or the soft plus, which is a smoother version of it. Now, these are just different ways of different kinds of functions that you can apply on this affine combination. The point being, at the end of it all, the perceptron, our basic unit, is just this structure which computes an affine combination of the inputs. What I mean by affine is a weighted combination of inputs plus an extra term. And then it passes this affine combination through a nonlinear function. The specific nonlinear function we've seen so far is the threshold, but you can have other kinds of nonlinear functions. We won't spend time on that. The multi-layer perceptron is a network of such perceptrons, and it's generally layered. Now, in saying this, when I say a multi-layer perceptron, and when I say generally layered, I've thrown a little bit of terminology at you, which is, what is a layer? What do I mean by a layer? Does anybody know the answer to that question? Anyone? How would you define a layer? Considering people seem to be listening. Yes, Shakil? I couldn't hear the answer. Can someone convey it?
Yeah, can you hear me?
Yeah.
Yeah, you actually, what you're doing, you're trying to, basically doing some matrix multiplication, and then you are, making it, stacking the multiplications inputs. So that's we consider it as a layer.
There's actually a very formal definition for a layer, right? So my question really was, what do we mean? What is this formal definition for a layer? Well, your voice was very muffled, so I'll answer it. All right, okay, yes, there were 2 other participants. Somebody will have to convey the answer to me. Yes, go ahead. If you can type it, someone can convey it, or maybe. The audio is very scratchy.
Hello?
Yes. Irene?
A layer, to me, I'm thinking it's just a combination of different nodes.
Not really. Okay. Anybody else? That's not enough. That's part of the answer, but not all of it. Yes. Okay, so let me answer, right? We keep hearing of deep networks. What do we mean by deep? That too is not clear, correct? So let's define deep first. If I have a directed structure, any directed graph, then the depth which has a source and a sink, or a source, it can have multiples, right? Then the depth of the graph is the length of the longest path from the source to the sink. So here, for example, on the left-hand side, I have a graph of 3 nodes. There is one source, one sink. There is a path which is only 1 hop long from the source to the sink. There's also a path which is 2 hops long from the source to the sink. So this graph has a depth of 2, not 1, although there is a path that is only 1 hop. The figure to the right, I have a graph with 4 nodes. I have a source, which is the first node. You have a sink. There's a path which is 1 hop long from source to sink. There's a path which is 2 hops long. There's also a path which is 3 hops long. This graph has a depth of 3. Is that clear to everybody? Raise your hands if that's clear. Pretty much everyone. Okay, fine. Right, this is easy. And so now you know what the depth of a layer is. Here's how I'm going to define a layer. I'm assuming that all neurons or the input is layers, the input can be considered as a single node. Then a layer of neurons is the set of all neurons that is the same depth with respect to the input. Yes, yes, Hector? What's the question? Oh, so this just raise your hand late, is it? Okay. So a layer is the set of all neurons, which is the same depth with respect to the input. Did that make sense to you guys? There's a very formal definition for layer. Right? And if you have a question, so for example, some of you have encountered ResNets. Now, ResNets have all kinds of shortcut links and such like, but then the notion of a depth and the notion of layer is very well defined, regardless of the fact that you have connections hopping all over the place, because a layer is the set of neurons which is the same depth with respect to the input. Now, a deep network is one where the depth of the output layer, which is the set of neurons from which we get outputs, is greater than 2. So that means you have at least 2 hidden layers whose outputs you do not see. Now, for the multi-layer perceptron, the inputs can be Boolean or real. The outputs can be Boolean or real. You can have a single or multiple outputs. So these are all generalizations of the basic network that we saw. The question we're going to address in the next hour or so is, what kind of functions can this network compute? What kind of input-output relationships can it model? We've already seen that an MLP can compose Boolean functions. It can compose any Boolean function. It can compose real-valued functions. But what are and it can compose classification boundaries, decision boundaries. So what are the limitations? Let's look at the Boolean functions first. How well do MLPs model Boolean functions? We've already seen that a simple perceptron can model Boolean gates. So this guy to the left, as we saw earlier, this is an and, this is a not, the one to the bottom is an or. We've seen this. Here is a more complex one. This is what I will call a universal AND gate. This one has n inputs, and it's only going to fire if the first L inputs are all 1 and the remaining inputs are all 0. For no other pattern will this fire. Now, if you want to understand why, take a look. Let's set it to the combination where it fires. I make the first L bits all 1, the remaining bits all 0. That means the total input coming from these lower half bits is 0 because their values are 0, regardless of these weights. The total input coming from the first L bits is L because each of them has a weight of 1. So when you have this in the appropriate combination, the total input is L, which matches the threshold, and so this is going to fire. But then now let me flip one of these bits, which was supposed to be 0. If I flip any of them to 1, that's going to contribute a -1 to the sum. So the sum will become less than L and it will not fire. Similarly, if any of the first L becomes 0, that is going to reduce the sum again. So the total sum is going to be less than L and it's not going to fire. So this neuron is a universal AND gate, which fires for a very specific, very complex combination of its inputs. Here's another. This is only going to fire if at least one of these first L bits is 1, or if at least one of the remaining bits is 0. That sounds complex, right? It means that if anything, if any one of x1 to xl is 1, or if any one of xl plus 1 through xn is 0, it's going to fire. All of those conditions would have to fail for this to not fire. So this is the universal OR gate. I can explain the logic here again. That's fairly straightforward. Let's set it to the one condition where it will not fire. It will not fire if all first L are 0 and all the remaining ones are 1. If all first L are 0 and all the remaining ones are 1, then the total input is going to be L minus n. If any one of them flips, then the sum is going to become L minus n plus 1. And so it's going to, so in any pattern except the one condition under which it's not supposed to fire, it will fire. So it's again, that's a pretty complicated function. Here's something more complex. This one has n inputs. It's going to fire if at least k of these inputs is 1. And you can immediately see why this is the case. The threshold is k. If at least k of these inputs is 1, the sum is at least k. But if less than k of the inputs is 1, then the sum is not going to match this threshold and it's not going to fire. So this is the universal, this is not a universal law, this is a majority gate. So what's called a majority gate. And it's going to fire if k of the inputs are 1, at least k of the inputs are 1. Now, this is a very complex function, right? Now, at least in the case of these ANDs, you can imagine a standard Boolean gate performing the same operation. But then if you want to perform this majority gate using a standard Boolean gates, not threshold functions, that will require an exponential number of gates to capture every single pattern under which k inputs are 1, k or more inputs are 1. Whereas you can perform this thing that requires an exponentially sized circuit if the gates are Boolean using just one perceptron. So the perceptron is much more powerful than a Boolean gate, which is why Rosenblatt got fooled. He thought it could compute anything. Now, it cannot. We know that it cannot compute an XOR, as Minsky and Papert showed. However, once you begin connecting them up into a network, you can compute an XOR or pretty much any Boolean function. That too we have seen. And again, reintroducing this notion of the hidden layer. The hidden layer is the set of all neurons in a layer where the outputs of the neurons are not directly seen, but just feed on to other neurons. So we realize that MLPs can compute, once you network the MLPs, because they can compute Boolean gates and because they can compute majority functions, you can compute any Boolean function. So MLPs are what are called universal Boolean functions. You give me a Boolean function, I can compose a multi-layer perceptron which computes it. So it's a universal Boolean function. But then here is the question, right? You see this hideous function to the left? It's a pretty ugly function. To compute this function, my network requires 3 layers. The first layer, which has all this, which is this guy here, and then the second layer here, and the third layer here. There are 2 hidden layers, right? In reality, how many layers do I really need to compute any odd Boolean function? What is the actual number of layers I can go down to compute any Boolean function? And that answer is 1. Let's see how. Now, what is a Boolean function? A Boolean function is just a truth table. Suppose I have a Boolean function of 5 inputs. So then I can compose a table of this kind where I have x1 through x5 listed here and the output y listed over here. And here is the interesting thing. There are 5 inputs, so there are 2 raised to 5, 32 possible combinations of inputs. But I don't need to list all 32 combinations in my table. It is sufficient for me to just list those combinations for which the output is 1. For all other combinations, the output is implicitly 0. So this table, although it has only 6 rows, it actually represents a full function over all 32 combinations of x1 through x5. That clear to everyone? Just raise your hand so I can keep going on. If I see 20, yes, everybody got it. Perfect. So now, when I want to compose a Boolean function for this guy, for this table, all I have to do is to write out a DNF formula for it. Now consider this first row. This first row says the output must be 1 if x1 is 0, x2 is 0, x3 is 1, x4 is 1, and x5 is 0. So I can write the Boolean function for it as not x1, not x2, x3, x4, and not x5. So under that condition, the output is 1. So also not x1, x2, not x3, x4, x5. Under that condition too, the output is 1. So for each of these 6 rows, I will get one such clause, and the output is 1 if any one of those clauses becomes valid. So the overall table is simply the first row, if the input is the first pattern, or the second pattern, or the third pattern, or the fourth pattern, or the fifth pattern, or the sixth pattern. Those are the conditions under which the output is 1. So I can write it as this first clause representing the first pattern, or the plus represents or, the second clause representing the second pattern, or the third clause representing the third pattern, and so on. So this DNF formula fully represents this Boolean function. And it doesn't matter how many inputs you have, how complex the Boolean function is, eventually it's just a truth table. And I can write the truth table in the form of a DNF formula. But once I realize that it's a DNF formula, I can use threshold gates and compose a very compact network. So I use one perceptron for this first clause, one for the second clause, third for the third clause, fourth for the fourth clause, fifth for the fifth clause, sixth for the sixth clause, or all of them. And voila, I have a one hidden layer MLP that computes this Boolean function. And because any Boolean function can be represented as a truth table, and because any truth table can be represented as a DNF formula, and because any DNF formula can be represented as a one hidden layer MLP, it means that it doesn't matter how complex the Boolean function is, I can compose a multi-layer perceptron with just one hidden layer, which computes it. So in other words, a one hidden layer MLP is a universal Boolean function. But then, how big will this network get? What is the largest number of perceptrons required in that one hidden layer for an n input variable function? For that, let's take a different view of truth tables. I assume that at least the electrical engineers amongst you have encountered Carnot maps. A Carnot map is just a truth table. So here I have 4 inputs, W, X, Y, and Z. And I've listed all combinations of W, X along the rows, all combinations of Y, Z along the columns. And the magic over here is that if you look at any 2 adjacent rows, they differ only in 1 bit. So this is 0, 0, this is 0, 1. This is 0, 1, this is 1, 1. 1, 1, 1, 0. And the whole thing actually loops. So this guy at the bottom actually is adjacent to the one on top. So although I've laid it out as in a line, you should think of it as a circle. So also every column, the columns represent all patterns of input Y and Z, but every column differs from the previous column in only 1 bit. So 0, 0 differs from 0, 1 by 1 bit, 0, 1 that differs from 1, 1 by 1 bit, differs from 1, 0 by 1 bit. And this guy in turn differs from 0, 0 by 1 bit. So this is the complete set of all input patterns, right? Every square over here represents a complete set of input bits, a full pattern. So this square represents the combination 0, 0, 0, 0. This square represents the combination 0, 1, 1, 0, and so on. The highlighted yellow boxes represent the input combinations for which the output is 1. And so here we have a total of 4 bits. So you have 16 boxes because you have 16 combinations of 4 bits. Of these 16 boxes, 7 are highlighted. So if I just wrote out a naive DNF formula, like the one I had previously, that DNF formula would have 7 clauses. And so if I were to just write this out as a DNF formula and compose a one hidden layer MLP for it, that one hidden layer MLP is going to have 7 neurons in the hidden layer. So the basic, but then there's something nice about how we lay things out in Carnot maps. Look at these guys. All of these guys are neighbors of one another. Now, the fact that all of these four are highlighted means that it does not matter what the WX combination is, so long as Y and Z take the value 0, 0, the output is 1. So I can group all of these neighbors and eliminate these two variables. So this entire group gives me only one clause, not Y, not Z, which means that the network will fire. The function gives you an output 1 if Y is 0 and Z is 0. Similarly, I can group these two guys. And when I group these two guys, it tells me that the value of Z does not matter so long as W is 0, X is 1, and Y is 0. So this group represents the clause not W, X, not Y. Similarly, I can group these two guys, and I'm going to get not X, Y, not Z. And so the actual DNF formula, although there are 7 blocks over here, I can compress this DNF formula down to just 3 clauses. And so this guy can now, the actual MLP, one hidden layer MLP for this Boolean function has 3 neurons in the hidden layer. So long as we can keep grouping things up in this manner, I can get very compact DNF formulae. And the number of neurons in the hidden layer is going to be exactly equal to the number of clauses in the DNF, in the most compact DNF formula for the Boolean function. But then, what arrangement of ones and zeros over here simply cannot be reduced by grouping? Does anybody want to give me a guess? Anyone? Nobody has you. Hey, this is an easy question. Yes, I see one. I can't hear you.
A chessboard?
Pardon me? A chessboard, exactly, right? This guy, right? So, because there are no neighbors. And so, because there are no neighbors, the only way, if I have a DNF formula for this, this is going to need 8 clauses. I can't group them. If I have an MLP with one hidden layer, it's going to have 8 neurons in that hidden layer. I can't reduce it, right? Now, let's consider a 6-input variant of it. I can construct a 3-dimensional Carnot map if I have 6 inputs. All the same rules apply. And now I can compose a truth table of this kind. Again, it's a 3-dimensional chessboard. There's no way I can begin grouping things together, which means that there are 32 red boxes. So my DNF formula is going to require 32 clauses. My one hidden layer neural network is going to require 32 neurons in its one hidden layer. I can generalize this. For n inputs, in the worst case, I'm going to require 2 raised to n minus 1 perceptrons in the hidden layer, which is exponential in n. So when I actually, in the worst case, if I want to build an MLP with just one hidden layer to model this Boolean function, that is going to require, for n inputs, it's going to require 2 raised to n minus 1 neurons, right? In the hidden layer, which is way expensive. But then, if I allow myself to use more than one hidden layer, how many neurons will I require for this guy? Anybody want to take a guess? Anyone? Okay, let me give you the answer. These two functions are very simple. That first function is simply W XOR X XOR Y XOR Z. The second function is U XOR V XOR W XOR X XOR Y XOR Z. And we know that for an XOR, we need only 3 perceptrons. We've already seen this. Which means that for this network, I can have first one XOR computing W XOR X, 3 neurons. The output of that can be XORed with Y, 3 neurons. The output of that can be XORed with Z, 3 neurons. This entire network has 9 perceptrons. For the 6 input guy, I have 5 XORs, right? Because there are 6 variables. This is going to require 3 neurons per XOR. So this will require 15 perceptrons. Now, you may not see the difference too much, but if you scale it up to n variables, the XOR of n variables will require, you basically only need n minus 3 neurons, 3 perceptrons per XOR. You need 1 XOR per variable. You don't need an XOR for the first variable. So you need 3 times n minus 1 perceptrons. And so you can see that if I just use a single hidden layer, this is going to require 2 raised to n minus 1 plus 1 perceptrons and all, because you need the final output neuron, right? This is the number of neurons that you will require to represent this function using a single hidden layer is exponential in n. On the other hand, if I compose a deep network, in the best case, the number of neurons is linear in n. The difference is enormous, as you can see. Exactly how deep do I have to be for this to work? You can even compute that. It turns out that the shallowest network that will compute this function in the number of neurons that's linear in n is 2 times log base 2 of n. How is that? Consider this guy, x1, XOR, x2, XOR, all the way to xn, right? The XOR is associative. So what I can do is I can XOR the first 2 guys, then I can, yes, Nick? I can't hear the question.
Sorry, yeah, sorry, I'm on a train, I'm sorry. Could you go back 1 slide?
Yeah, sure.
So to your point about the expressivity of single layer,
your voice is dropping, Nick.
Hidden neural network. Is there any deep relation with Gaussian processes in this finding?
Degradation and what, pardon me?
Is there any deep relation with Gaussian processes, which can also be
deep relation with Gaussian processes? You are speaking
correct.
of, I'm speaking of Boolean networks over here, but all of these concepts translate to pretty much, yes, all kinds of processes, and you will see by the end of this lecture. In the terms of the the optimal number of the optimal depth of the hierarchy of any model is going to be the minimal depth to get not too many parameters is going to be dependent on, logarithmically dependent on the number of inputs.
Thank you.
Yeah. So, or at least logarithmically. Again, these are all bounding cases, right? I'm giving you extreme cases. So here, now look at this one here, right? So I can group the first 2, x1, XOR, x2. Then I can compute x3, XOR, x4. So I can compute XORs by pairs. And that's going to be this layer here. Then I can compute XORs by pairs again and keep doing this all the way to the top. So basically each XOR requires 2 layers. So I have this factor 2, but because I'm doing it in pairs, I just need, if I have n inputs in all, the number of layers is going to be log base 2 of n. So the total number of layers of this network is simply going to be 2 times log base 2 of n. If I have a network of at least this depth, then I can always construct it to compose this XOR function using a number of neurons, perceptrons that's linear in the dimensionality of the input. On the other hand, if I truncate the depth beyond that, so let's say I just say, I give you an upper bound and I say you're not allowed to construct a network that's more than 6 layers deep, then what is the best you can do? You can use the first 2 layers to get an XOR, the first 4 layers to get two layers of XOR. Then you have the output neuron itself. And then the 5th one is going to be a computing on XOR on the outputs of the 4th layer. And you're trying to compute this complex XOR using only 1 hidden layer at this point. And that hidden layer is going to become exponentially wide. So anytime you put a limit on the number of layers in the network, then what you can do is compute XORs until just below the limit. But then what follows is still going to be an XOR, and you're computing a very complex XOR function. with just one hidden layer, and so the number of neurons in that layer is going to blow up. So that makes sense to everybody? Raise your hands. Yeah, perfect. So reducing the number of layers below the minimum will result in an exponential size network to express the function fully. A network with fewer than the number of neurons or fewer than cannot model the function, and the number of neurons required is going to depend on the depth of the network and can increase exponentially as the size and the depth of the network decreases. So deep Boolean MLPs that scale linearly with the number of inputs can become exponentially large if recast using only one layer. And it gets worse. You can have some very complex function which eventually becomes an XOR of some variables. At that point, you need further depth. If you try to terminate the depth from that point on, you will get an exponential blow up in size. So having a few extra layers can greatly reduce network size and the number of parameters. Now, there was a little bit of hand waving over here. The XOR is really a parity problem. And there is a great deal of math on parities that I'm not going to go over, so I'll just skip that. But here is the point. An MLP is a universal Boolean function. We've been speaking of Boolean inputs. It can represent a given function only if it is sufficiently wide, if it's sufficiently deep. Depth can be traded off for exponential growth of the width of the network. Optimal width and depth depend on the number of variables and the complexity of the Boolean function. Not every Boolean function is going to grow up, exponentially in size. We specifically looked at the parity function because that was some kind of a worst case. And the complexity of the Boolean formula really governs the size of the network, where the complexity is the minimal number of terms in the DNF formula for the function. And as it turns out, trying to even determine the minimal sized DNF formula for a Boolean function is an NP-hard problem that cannot be solved. And so we're just better off building deep networks as opposed to trying to find out the optimal shallow network. So the story so far is that multi-layer perceptrons are universal Boolean machines. Even a network with a single hidden layer is a universal Boolean machine, but a single layer network may require an exponentially large number of perceptrons. Deeper networks require far fewer neurons than shallower networks to express the same function. They could be exponentially smaller. I'll actually skip this. I have some slides here which are supposed to be hidden, but somehow they're not. Please look over the slides in the slide deck. As I promised I'd keep the math out of this as far as possible, so I shall do so. Now, we've seen MLPs as Boolean functions. We saw MLPs can be Boolean functions, they can be classifiers, and they can be real functions. So let's look at case number 2, where they are classifiers, right? Now, in the case of classification, the MLP is a function over real valued inputs, and it finds a complex decision boundary over the space of reals. So here's what the perceptron does. The perceptron computes a 1 if the affine combination of inputs is positive. It outputs a 0 otherwise. The boundary between the two is a hyperplane or a line in the two-dimensional case. And the output is going to be a 0 on one side and a 1 on the other side. So the perceptron is a linear classifier. The boundary between the region it designates as 1 and the region it designates as 0 is a linear surface, a line or a hyperplane. And once we saw that, once we know how to compose a perceptron of this kind, which outputs a 0 on one side of a line and a 1 on the other, we can compose more complex decision boundaries like this pentagon. We want the network to fire if the input is in the color in the brown area and not otherwise. So the way we did it was to have one perceptron for every edge. We summed their outputs. The sum was 5 only inside the pentagon. It was less than 5 outside. So if this final perceptron uses a threshold of 5, it will perfectly give me a decision boundary that's a pentagon. Now, I don't want you to imagine that this means that the network can only capture convex regions like pentagons. Can somebody tell me how this same network, without changing anything except a threshold, can give me a star-shaped decision boundary? I'm changing nothing. It's the same network. All the parameters are the same. You're allowed to change one parameter in the network, which is a threshold. Yes, Samada?
Yeah, so you only change the threshold into 4. You got a shape of star.
Exactly. You change the threshold to 4. Now you get a star-shaped decision boundary, right? So again, don't get fooled into believing it only models convex shapes. But then the point is, once we know how to model convex shapes, we can model more complex shapes like this guy here, where I'd use one subnet to capture the first pentagon, one for the second or the two, and voila, I get this double pentagon, right? But to do this, I needed 2 hidden layers and 1 output layer. So I needed a 3rd layer. And if I use 3 layers, I can sort of decompose pretty much any decision boundary in this manner and construct a network for it. So for example, to get this crazy decision boundary here, I could decompose into all of these little polytopes, have one subnet for each polytope or their outputs. And I get my crazy decision boundary, disconnected, ugly, non-convex decision boundary. And I do it very simply, right? But then my question is, can we do the same thing using only 1 hidden layer? Actually, let's take a simpler problem. I want this double pentagon decision boundary. How are you going to capture it using only 1 hidden layer? Anybody have any ideas? I want a network of the kind that I have to the right. It has 1 hidden layer, and I wanted to capture this double pentagon decision boundary. Any ideas? Is Samada?
I think we need at least 10 or exactly 10 perceptron.
You think you can do it with 10?
This is the first thing that came to my mind, that you need a perceptron for each edge.
Yeah. It doesn't quite work out that way. So what will happen is that with 10 perceptrons, you are going to get these double pentagons, but you're going to, regardless of how you do it, you're going to end up with other regions being included in the yellow. If you try working it out, you will see that happens in every single case. The actual answer is infinite. So to explain why, let me back off to a much simpler decision boundary. I want a diamond. If I want a diamond, I'm going to use 4 perceptrons, and I'm going to look at the sum of the 4 perceptrons and compare it to 4. Now look at the sum. The sum is 4 inside the diamond, but it's 3 just outside the diamond, right? And the region where the sum is 3 has infinite area. Now, suppose I go up to a pentagon with 5 sides. Then I can do this with 5 neurons. The sum of the 5 neurons is going to be 5 in here. It's going to be 4. It's going to be 4 in these little triangles. It's going to be 3 in these other regions. It's going to be 2 in yet other regions. It never goes below 2. But here is a key thing. Here, n was 4. The number of sides was 4. The area of the region where the sum was n minus 1 was infinite. Here, n was 5. The number of sides is 5. The area where the sum is n minus 1 is finite. Where the sum is n minus 2 is now infinite, right? If I go up to a hexagon, then the area where the sum is n minus 1 becomes smaller still. I can get a hexagon with 6 neurons in my hidden layer. And the sum of the 6 hidden neurons will be 6 inside the hexagon and 5 inside each of the triangles. So as we keep increasing the number of sides in the pentagon, you're going to begin seeing a pattern. These figures are kind of broken because of, matplotlib. But in this case, I have 7 sides. The sum is 7 over here. You see this little orange thing? In those regions, the sum is 6. In this beautiful star, the sum is 5. Here, the sum is 4. And in these little valleys, the sum is 3. If I go up to 16 sides, the sum is 16 inside here. These little orange regions are where it's 15, this is 14, this is 13, this is 12, this is 11, this is 10, this is 9. What do we observe? As you keep going up, the area, the area, or rather the volume of the space within which the sum of the hidden layer neurons is less than n, but greater than n over 2, keeps becoming smaller and smaller and smaller. Here it is with 1,000 sides, right? So increasing the number of sides reduces the area outside the polygon where the sum is between n over 2 and n. Does this make sense to everyone? Yeah. So in the limit, you can actually work out the formula, right? This is what it's going to look like. As n tends to infinity, if you sum the outputs of all of these hidden layer neurons, the sum is going to end up looking like this with a perfect, almost perfect circle on top where the sum is n, and then it's going to fall off very quickly to n over 2, according to this formula. And for small radiuses, this figure is going to be almost perfectly a cylinder, where the sum is n in the cylinder, exactly in the cylinder, and exactly n over 2 outside. So you can design the circle to be of arbitrary diameter centered at any point, but in the limit, as n becomes very large, as n approaches infinity, the sum of the outputs of the neurons in the hidden layer is going to end up looking exactly like a cylinder with n over 2 outside and n inside. If I add a bias of minus n over 2, then the sum is going to become 0 outside the cylinder and n over 2 inside the cylinder. Now observe that the sum is being obtained. There is no activation for this final guy. All I'm doing is summing these outputs. And when I sum these outputs, that output as a function of the input looks like a cylinder. So suppose I take 2 such networks, one of which composes a cylinder at the bottom left here, and the other composes a cylinder at the top right. Now, because this is just a summation without any activation, I can sum the 2 outputs, sum the outputs of the 2 networks, and that is simply going, one subnet is going to be directly, so one subnet is going to be this set of neurons, which produces the first cylinder. The other subnet is this set of neurons, which produces the second cylinder. The sum of the outputs of these 2 networks is going to be a double cylinder. Again, no activations applied. If I just sum all of these guys, I'm going to get a double cylinder where the output is 0 everywhere, except in these 2 cylinders where the output is n over 2. And so now I can apply a threshold of n over 2, and I'll get a decision boundary, which is exactly 2 circles. And now that I know how to compose a decision boundary that is the union of 2 disconnected circles, I can compose my double pentagon by just filling it up with circles. And if I make the circle smaller and more compact, then my approximation to the double pentagon is going to get more and more precise. And so I can achieve arbitrary precision in modeling my double pentagon. In other words, MLPs are universal classifiers. Single hidden layer MLPs are universal classifiers, but approximately universal classifiers. Even with just one hidden layer, I can approximate any decision boundary, but there's a trade-off, right? When you look at what you got with 2 hidden layers, I just needed 11 neurons in all, right? No, 5, 10, 11, 12, 13 neurons in all. Whereas if I wanted one hidden layer, I needed infinite neurons. So simply reducing the depth by 1 exploded the size of the network to something impractical. So deeper networks, so a single hidden layer network is a universal classifier, but deeper networks can require super exponentially fewer neurons. Now, that was for a very simple problem, right? Let's look at a slightly different pattern to understand how depth and breadth trade-offs happen. And so I'm going to look at some kind of an approximate worst case decision boundary, and I'm going to use threshold activation units. So let's say I want to have this decision boundary to the right. A one hidden layer neural network will require infinite hidden neurons. We already saw that. I can get this boundary if I use 2 hidden layers using only 56 hidden neurons. Why is that? This entire checkerboard pattern, I want this decision boundary. I want the neuron to output a 1 if the input is in the yellow regions. It's a 2-dimensional input. I want the network to output a 0 if the input is in the gray regions. You'll observe that the entire pattern is composed of 16 lines. So I need 16 neurons in the first hidden layer, and each neuron will tell me which side of any line the input is on. But there are 40 of these yellow regions. And so I will need 40 neurons in the second layer, combining the outputs of these 16 first layer neurons. And each of the neurons in the second layer is going to tell me if the input is in one of these yellow regions or not. And then I OR the entire lot, and I get this decision boundary. So this entire structure can be obtained using 57 total neurons. But then think about this. This pattern is just, once I capture the lines, if I have 16 variables telling me which side of each of these 16 lines the input is on, then this pattern is just y1 XOR y2 XOR all the way through XOR y16. So there are 15 XORs. I can do this with 15 times 3, 61, and 45 neurons for the XOR plus 16 neurons for the lines. So I can do this with only 61 neurons. Again, when I did this with 2 layers, I needed 56 neurons, not 52. But if I do this with an XOR network, it requires 61 neurons. You think you may have lost. But if I make the problem more complex, you can see the gap quickly beginning to show up. So suppose I were looking at this particular structure, decision boundary. With 1 hidden layer, I'm going to need infinite neurons. But this decision boundary is composed of 64 lines. So I will need 64 neurons in the first layer. And then there are 544 boxes, yellow boxes. So I'm going to need 544 neurons in the second layer. And so including the output neuron, I need 609 total neurons. On the other hand, this is just an XOR over the 64 lines. So if I compose an XOR network with 12 hidden layers, this can be done using only 253 neurons. So as the pattern becomes more complex, even in 2 dimensions, the difference between the shallow network and the deep network will increase rapidly, exponentially. So what we have is that MLPs are universal Boolean machines. Even a network with a single hidden layer is a universal Boolean machine. They are universal classification functions. A network with a single hidden layer is a universal classifier. But a single layer network may require an exponentially larger number of perceptrons compared to a deeper one. Deeper networks may require exponentially fewer neurons than shallower networks to express the same function. And they could be exponentially smaller, so they are more expressive. That's the story so far. But then let's continue and wrap this up, right? We were looking at decision boundaries. We are looking at Boolean functions. What about continuous valued regression? Now for regression, the output is real valued. We saw that when I'm looking for a scalar function of a scalar input, a simple 3-unit MLP with a summing output can generate a square pulse over an input. We saw that an hour ago, right? And then I can combine a whole lot of these up to compose any arbitrary scalar function of a scalar input to arbitrary precision. But then if I have a multi-dimensional input, things get a little more complex, not very much. We know that with infinite inputs, infinite neurons in the hidden layer, an MLP can compose a cylinder where the function has, where it's the value is n in the center and n over 2 outside, or n over 2 in the center and 0 outside, if I include the bias. So now suppose I want to compose an arbitrary surface. What I can do is to plug in, place an arbitrary number of cylinders under the surface and adjust their heights, and such that I can now approximate the function by this set of cylinders. And so any arbitrary function can now be approximated by a multi-layer perceptron with only one hidden layer by approximating it as the surface itself using a union of cylinders. I can approximate it to arbitrary precision by making the cylinders thinner or thicker and increasing the number of cylinders. So an MLP is a universal approximator. Even just a one hidden layer MLP is a universal approximator. But then we've been talking about depth. Clearly, using infinite neurons is not a great solution. You want to have a finite number of neurons, and to have a finite number of neurons, you require depth. Deeper networks will require far fewer neurons than shallow networks to express the same function. Right. So here's where we stand. Single layer MLPs are universal function approximators. They can approximate any function to arbitrary precision, but may require infinite neurons on the one hidden layer. More generally, deeper networks will require far fewer neurons for the same approximation error. The network is a generic map, and if you're just looking for continuous valued functions, all of the principles that apply to the Boolean network also apply here. You can require exponentially fewer neurons for deep networks than for a one-layer network. Now, here's a final bit on what other restrictions are there besides that we like the network to be deep. So for that, we have to sort of visit this notion of capacity, which we alluded to at the beginning of this network. Let's go back and look at this simple pattern again. I want to build a neural network that captures this decision boundary. The output is 1 in the yellow regions and 0 outside in the gray regions. Was there a question? Right. So a network can represent this function, but it needs sufficient capacity. It needs to be sufficiently broad and sufficiently deep. Otherwise, it cannot represent this function. To explain, let's say we know that we can model this with 2 layers, with 16 neurons in the first layer and 40 neurons in the second layer. But suppose I give you only 8 neurons in the first layer. What happens? Assuming I'm using threshold activation functions, there's no way I will be able to model this classification, this decision boundary, regardless of what you do in the second layer. If I give you only 8 neurons in the first layer, I can give you infinite neurons for the second layer. You cannot model this boundary. Why is that? When I'm using threshold functions, each of these guys models a line. So it's going to tell me whether I'm on the right of this line or the left of the line, right? So let's say I have these 8 neurons, and these 8 neurons captured these 8 lines. The information to capture transverse patterns has already been lost by the time you cross these 8 neurons. You will never ever be able to capture. You can say how you vary along this axis that I'm moving the pointer along, but you have no information about how you are moving in this direction once you cross the first layer. So you cannot the information is lost. You can have an infinite neurons in the second layer, you remain screwed. Even if the first, even if the first layer neurons give you this hash, so somehow the first 4 of these neurons captured these four lines, the remaining 4 captured these 4 lines. It doesn't matter. Once you get past the first layer, if you're using threshold activations, the neuron only tells you whether you're to the right of the line or to the left of the line, but it doesn't tell you how far away you are from the line. So the actual information that you capture is only going to tell you, the output of the first layer neurons will tell you which of these boxes you are in, but will not tell you where you are inside the boxes because you're using threshold activations. As a result, I can give you any number of neurons in the second layer. You cannot capture the finer grained decision boundary, a golden and gray decision boundary, if you have only 8 neurons in the first hidden layer. So same thing. Let's say I go ahead and give you 16 neurons in the first hidden layer. So the 16 neurons have captured all 16 lines. But then now I give you only, say, 10 neurons in the second hidden layer. There's no way you're going to be able to capture this decision boundary. There are 40 boxes. You will need 40 neurons in the second hidden layer. Yes, Pranav? What is the question? I can't hear you. You're going to unmute yourself. Can someone convey the question? Let's wait for the break, right?
Yeah.
So in this setting, if there are 40 boxes and I give you only 10 neurons in the second hidden layer, unless the first hidden layer becomes extremely wide, infinite, for any finite width of the first hidden layer, with only 10 neurons in the second hidden layer, you will not capture this pattern. There are 40 boxes. 10 neurons are not going to capture it. So you see the point that if any one of the neuron layers has fewer neurons than required to capture the basic minimum number of units, it doesn't matter how much you try to overcompensate in the other layers, you cannot capture the pattern. And why is that? For the specific case of threshold units, I've been talking about threshold units. What happens is that a threshold activation gates information. So a neuron over here will tell you if you are to the left of a threshold or if you're to the right of a threshold. So it may tell you if you're in the blue region or on this side, but it won't tell you how far you are from the boundary. So each of these 4 guys will capture 4 of these boundaries, but they will not give you any information about how far you are from the boundary. So you could be anywhere in this yellow region, and the information received by the second layer neurons is the same. There is no distinction, so there is no information to make finer grade distinctions to be able to add extra decision boundaries on top of what the first layer captured. So it means that for this to work, the first layer neurons absolutely have to capture all the necessary basic boundaries for higher level neurons to be able to compose the full complex decision boundary. But there's a workaround, right? What happens if instead of using a threshold activation, I use a continuous valued activation like a sigmoid? Now the continuous valued activation gives you graded output. When it gives you graded output, it will actually tell you how far away you are from the decision boundary. And so as a result, the second layer neuron not only knows which side of the decision boundary you are on, it also has some information of how far you are from the decision boundary. And so now it has information that it can use to construct additional patterns. Now, of course, if you're using a sigmoid, this information is present for only a very short distance. Once you go past the distance, the sigmoid saturates in either direction, and the information is lost. And so a sigmoid activation is probably not the best activation. You want graded, you want the activations to be graded away from the decision boundary. And only in that case will you get away with having fewer than the required number of neurons in the lower layers. And so suppose I were to give you 3 activations. One is, can I have a different color? Let me see, in color green, right? So I have 3 activations. One of them is this threshold. That's a threshold function, that's mine. One of them is this ReLU, the other is the soft plus, and the fourth one is something like this, which is what they call a leaky ReLU. Of the 4 of these, which of them is going to be most useful if you want to use a small number of neurons in the first layer? Anybody want to answer? Anyone? At this point, I suspect the audience is gone. Anyways. Yes, Geet.
I think leaky ReLU captures most of the information.
Yes, because it tells you, the ReLU only tells you how far you are in one direction, but it misses the other direction. The leaky ReLU gives you information about how far you are from the boundary in both directions. So clearly the preferred activation over here is going to be the leaky ReLU. So narrow layers can still pass information to subsequent layers if the activation function is sufficiently graded. But then when you have narrow layers, you're going to have to, the information is being passed on, but you are passing some of the job also down to the lower, deeper layers. So you're going to have to compensate with greater depth to permit later layers to capture patterns. So in other words, your network needs to have a sufficient architecture. When you say sufficient architecture, there are 3 variables to this architecture. It needs to have a sufficient number of 2 variables. It needs to have a sufficient number of neurons in every layer of the network. 3 variables. It needs to be sufficiently deep to capture the patterns that you want, given your given whatever budget you may have for the number of neurons. And it needs to have the appropriate activation functions such that enough information is passed on, such that a pattern or information that's missed by one neuron can still be captured by other guys. So the network capacity, which is a function of all of these, must be sufficient to model your function. Now, the problem is it's really hard to quantify this network capacity, except in very simple cases like where you have threshold activations. And so you have various definitions for network capacity, like information or storage capacity, VC dimension. Yes, Nick?
Holding all other factors equal, does it follow then that for given configuration that the expressivity?
I'm sorry, can you speak closer to your mic again?
Yes, sorry. Does it follow that holding all other factors equal that the expressivity of a given neural network is higher using ReLU or 10H compared to logistics?
No. It just means that for the network is always trying to model the function. And whether you're using a TANH really, the problem with TANH and sigmoid, as you can see over here, is that you begin to lose information very quickly, not very far from the boundary. Leaky ReLUs continue to carry information far away from the boundary. So it has to do the ability to represent functions and pass functions down and to learn to model particular functions is going to depend on the activations. But a lot of how these activations influence you has more to do with the ability of the network to learn a function rather than some inherent limitation on the capacity of the network itself.
Thank you.
You can always increase the number of neurons to make up the things, right? So this is the VC dimension of a network is only a lecture. So the lesson so far, MLPs are universal Boolean functions, they're universal classifiers, they're universal approximators. A single layer MLP can approximate anything to arbitrary precision, but this could be exponentially or even infinitely wide in an input size, and deeper networks can achieve the same precision with far fewer neurons. They're more expressive. So I am going to stop right here, and I'll give everybody a 10-minute break. I'm skipping a few slides. Please take a look at those slides. And I'll jump to part 3 in 10 minutes. By my time, it is 7:33. We will meet again at 7:30.
7:45?
45, yeah.
Okay, cool.
Hui.
Hi, Bhiksha.
Oh, hi, I'm back.
Can you hear? Nice. So there are like around 8 questions.
Okay.
That I can maybe go through. The first one is, let's see. Okay. Do all the neurons in the same layer have the same function for deep learning?
Not, right? Because as we saw over here, I mean, look at let's consider the pentagon example. Each neuron is capturing a different line. Right? A line is effectively a different feature, right?
Nice. Oh yeah, I think okay. Next one. Well, okay, this one needs a specification. I think the one from Elisa. Like, in the meantime, please add the slide.
I check, and it's slide 89 from Elisa. So, yeah, it's about the Boolean function, the AND gate in slide 89. So she's asking if you change. So you say that from until XL. So can you go to slide 89? It might be easier if we look to the slide, because there's some notation.
Slide 89 is way back, right?
Yeah, it was.
I was just hoping I didn't have to go back that far. It takes a long time, yeah. I have too many slides, that's my problem. At some point, the slide numbers disappeared. So tell me when to stop.
I think.
Okay, I've already passed 70, 73, 89, right?
Yes.
This one.
Yeah, one of those. Yeah. So the perceptron. So the question is, if you change one of the neurons that are above L, so if that is still the AND gate is still true. So it's the other one with the AND gate. This is the OR gate. This one. So you say like the first half, yeah, up to L, yeah.
So should you want to understand how this worked?
Yeah, she's asking if you change one of the neurons from L plus 1 to N to 1, and one of the ones from 1 to L to minus 1. If this
it will mean, so basically all the inputs for which the weight is 1 must be 1, and all the inputs for which the weight is minus 1 must be 0. I just arrange them this way.
Yeah.
Right. That's about it.
Yeah. So the order doesn't. Yeah. They can swap it. Okay. Cool.
And the next question is in slide 139.
Okay.
On the question, okay, let's go first to 139.
Tell me when to stop. The numbers are missing.
Sure.
Yeah.
It's a bit.
Oh, sure. It's flying.
Okay.
That one. Yeah.
Yeah. 39.
Okay.
Okay. So the question is, why are the rectangles equal to 3?
So the sum, right? So take a look at this guy. Now, if you look at this region, right? For this region, the perceptron which captured this boundary. The perceptron which captured this boundary, that output a 0, everything else output a 1. Right? So consider this one guy. This perceptron output a 0, the remaining 3 output a 1. So the sum of their 4 outputs is going to be 3 in this region. So also over here, the perceptron that captured this boundary, that's going to output a 0, but the others are going to output a 1. So the sum is going to be 3. That clear?
It looks like it, because there's no answer, but yeah, it was clear to me at least. Okay, so another question is from Shaquille. Is there any reference to this material?
For this material? Only my slides. I spend a lot of time. This is a synthesis of a lot of material, right? I'm an old timer. I've been around since the early 90s, late 80s is when I went to college. So The stuff that I've got is something that's been synthesized from so many different sources. I don't think I can point you to any one source.
Okay. The next question is, when and why is it better to use activation functions that propagate less information, such as ReLU or leaky ReLU?
So when is it better to use an activation function that, I missed the second half.
That propagates less information.
Provides less information.
Yeah.
ReLU versus leaky ReLU, is it?
Yes.
I'm pretty sure there are cases where you can think of that. I mean, imagine a case where the function that you're trying to model is exactly a rectified linear unit. Then trying to model it using a leaky ReLU is going to be very hard, right? You'll need a much more complex function, whereas a simple ReLU would have captured it. So pretty much every statement that I make, you can find exceptions. The obvious thing being, for instance, if I'm trying to model a soft plus using a ReLU doesn't make sense. I should be modeling using a soft plus. So the statements I'm speaking of are generic, but there are many situations where, for example, if you have strict cutoffs, if the output is going to go to 0, then having activations that never go to 0 is not a very useful thing to do, right?
So it's still a matter of trying what works best, I guess.
So your best guess is, the point is, in most of the problems, if you're trying to approximate a specific function where you know that there are flat regions and non-flat regions and so on, then having activation functions which have flat regions kind of makes sense. But the most generic case, you have no information at all about the function that you're trying to model.
Exactly.
So in that case, your best guess is always to have an activation function which is graded on both sides.
Oh, nice.
I mean, you can always compensate for it by having many more neurons, right? So our leaky ReLU is the equivalent of 2 ReLUs, one pointing right, one pointing left.
Oh yeah, that's right.
Right, so you can always compensate for it by having 2 neurons.
Interesting. Thank you. And then there's 3 more questions. I see. One is, does the fact of deep neural networks being able to model more complex functions also means they overfit more easily?
So yes and no, right? So let me explain this. Guys, I'm going to sort of terminate the third portion of my lecture short, abruptly, because I won't have time, but let's take a look at what it means to learn a network, right? So when I'm trying to learn a network, I'm trying to learn a network that captures a function of this kind. But all I'm giving it are training data points, which give you input-output relationships. So I'm trying to learn this mesh, but I don't give you the entire mesh. I just give you a certain number of training points, like these red lines, where for each input, I give you the output. You try to fit the network at these points, and you hope that it learns the entire function, correct? And the way we do it, of course, we just sort of use backprop or whatever else. The problem is there is nothing stopping you from learning a function of this kind, which matches exactly at the red points and nowhere else, which is completely off. And now, this is a problem, right? But then let's go back and consider how much data you are actually providing to your network. I don't care what the size of the network is. I don't care what the size. I'm only worried about the dimensionality of the input. Consider a problem where I'm trying to do a binary classification on 10 cross 10 images. So basically 100 pixel images. These are 100 dimensional inputs. Each pixel is either 0 or 1. So it's extremely coarse. I'm taking a very simple problem, right? So that means that I have a binary 100-dimensional input. I'm trying to learn a function on this binary 100-dimensional input. Each of these input patterns is basically one of the corners of my unit hypercube, because every bit can be either 0 or 1, correct? So all of my inputs are going to be on the corners of this hypercube. So I'm making it very simple. How many corners do we have? You have 100 dimensions. Each dimension can take 2 values. There are 10 raised to 30 possible corners. If I want to fully specify the function, I have to specify the function at every single corner. Take a look at that picture. If I simply give you the value of this function at this one cube, you have no clue what the other 7 corners are, do you? You just don't. So giving you one data instance is like giving you no data point at all. You can fit that one thing. You can, to learn this function over the entire cube, you're going to need all 8 values. If I have 100-dimensional binary input, which is very, very, very small in the scheme of things, even MNIST is 730 dimensions, right? If I give you 10 raised to 15, that is 1,000 trillion training instances. I'm giving you 1,000 trillion training instances. Nobody gives you 1,000 trillion training instances. So this is a hypothetical situation. If you had 1,000 trillion training instances and you were trying to learn a function on this 100-dimensional binary input, you would have 10 raised to 30 corners for which you have to learn the function. You're given 10 raised to 15 training instances. Basically, you're given no training data at all. 10 raised to 15 means you're off by a factor of 1,000 trillion. So to give you a better idea, if I say I made this hypercube of a finite size, finite edge size, and then I put you in a little spacecraft, and I sat you on a corner of one of these, on one of these corners in the spacecraft, and I gave you the rules that you're only allowed to travel along the edges of the cube. It doesn't matter that you travel very near the speed of light. If you start from that corner and begin traveling around the cube randomly, the Earth will end before you hit your first training point. That's how rare your training data are compared to what you're trying to learn. So you're always overfitting. It doesn't matter what you do, you're always overfitting. If I scale things back logarithmically, you're literally giving a person 1.000000001 points per dimension and asking them to learn the entire function. Just gives you the scope, the scale of how bad this situation is every single time you attack a machine learning problem. Did any of that make sense to you guys?
Yes, that was very clear.
Mm-hmm.
Thanks, Bhiksha.
Yeah.
Thank you.
What was that?
So there are a couple questions, but I don't know if we have time for it or. Okay, thanks. The next question is a quick one following I think one that has been discussed. With a better activation function, can we reduce the number of required neurons or layers?
Absolutely right. That's what we discussed. In that, if you have an activation function that passes more information, you can get away with narrower layers, but you're going to have to trade off for depth. But then we also know, and here is something beautiful, right? Here, let me explain how depth works. In this example, I'm trying to learn these 2 decision boundaries to the left. One of them, you want a 1 if the input is inside the arrow, 0 outside. In the other, you want an input if one of the input is inside that white square with the hole in the middle, and you want a 0 outside, right? I know the optimally sized network. I can model this arrow as the union of a square and a triangle. So I need a 3-layer network where I have 7 neurons in the first layer, 2 neurons in the second, and 1 in the output layer, right? Same thing over here. I need 12 neurons, 8 neurons in the first layer, 2 in the second, and an output neuron. I know the architecture. I start off with the correct architecture. Then I randomly sample 1,000 training points from here and 1,000 training points from here. I use every single training trick known to mankind and try to learn the parameters of the network. What decision boundary does it learn? You see these 2 figures to the right? That's the junk it learned. Now, I didn't run it. I had an undergrad in Berkeley do it for me. But so, if there are problems here, you got to blame the guys in Berkeley. But anyways, you get the idea. It's really hard to learn these things. Where does depth come in? So I took a couple of very simple problems. One is the decision boundary to the left. I want a 1 if the input is in the black region, 0 outside, and the other one to the right, where I want a 1 if the input is in the bear-shaped region and 0 outside. In all cases, in all of these 8 cases, I have 660 neurons. In this case, we used ReLUs. We arranged the 660 neurons in 3 layers of 220 neurons each. Here, we arranged them in 4 layers of 115 neurons each. Here, we arranged them in 6 layers of 4 layers of 165 neurons. Here, we arranged them in 6 layers of 110 neurons each. Here, we arranged them in 11 layers of 60 neurons each. Now, as I increase the depth, the actual number of parameters falls very rapidly too. Do you see what's happening? For the same number of neurons, just rearranging them depth-wise as opposed to breadth-wise makes a tremendous difference to what it can learn. So why is that the case? This has to do with regularization. When I have 2 layers of a network with 2 layers, the second layer can only work on the functions that are output by the first layer. So the first layer has already smoothed out what is being presented to the second layer. And so as I keep increasing the number of layers, the later layers see smoother and smoother, basically learn smoother and smoother functions. And as a consequence, you actually get this natural regularization as you increase the depth of the network, as opposed to increasing the breadth of the network for the same number of parameters or the same number of neurons. In every single case, you can run all the empirical tests, you can run toy experiments. You will see that rearranging the same parameters depth-wise as opposed to breadth-wise wins you a lot. And this has to do with the fact that when you stack them up, the previous layer has already smoothed out stuff. So you're giving the next layer less flexibility to learn things. And that just works. Now, this only works if you have the appropriate activation functions. In this case, this works with ReLUs. If I replace this with sigmoids, it doesn't work. I don't know if that answered the question, but yeah.
It was very, very insightful.
Yeah.
And then the last question is, can dropout lead to less information being propagated down the layers, thus affecting the complexity captured by MLP?
So I don't have the dropout slides over here, but then dropout does something very different, right? Here, let me try to draw something. And maybe, just maybe this, it's really hard to draw with the mouse. So suppose I have neurons of this kind, correct? And so let's say I have 4-dimensional input. And I'll give you an extreme example. So my first layer is of this kind, where I have all 4 neurons connecting to all 4 neurons. Now, what is the restriction you're imposing on the model during learning to prevent it from simply learning something of this kind, where the first layer simply acts as a pass-through and passes the information down, pushing the task of learning on the rest of the reduced network? Do we have any restriction, any kind of regularization, if you're not using dropout, any kind of constraint that prevents this from happening? Do we have it? Anyone? Well, let me answer you. You don't, right? So what does dropout do? When I drop out some of these guys, then basically this information, you're basically preventing the information, or actually not these guys. When you drop out some of these guys, you're preventing this kind of pass-through being learned. And so you're basically ensuring that each neuron now learns a richer, more redundant pattern. That's basically the purpose of dropout over there. It prevents learning, nonsensical learning of this kind, and sort of statistically ensures that you end up learning richer patterns of this kind. That each neuron ends up learning richer patterns, which makes the whole classification more robust in some sense, and also ensures that you utilize the full capacity of the network, as opposed to doing something like this, where the capacity of the first layer is just lost. Did that answer your question?
There is, I'm sorry, but it was, yeah, it was very, very clear. Thanks a lot, Bhiksha. Oh yeah, it is. Thanks.
Any other questions?
Well, like just Shaquille that missed your answer about the references for your slides.
My slides. Unfortunately, I wish I had something. Those figures, you're not going to find them anywhere, for instance, or those examples.
Yeah.
They're
It would
like
be great if.
They're like 5,000 papers on the parity network and 5,000 papers on threshold networks, and that's probably an undercount. But, yeah.
Maybe it's time for a book.
Something of this kind, yeah. Probably.
Writing a book. Thank you, Bhiksha.
So I'm going to stop. Unfortunately, I have to stop at 3:30 my time, because I have another meeting at 3:45. So I don't know if I'll be able to get anywhere close to the rest of the slides, but I'll give it a shot, okay? Now, here is the continuing with the business of learning, right? How do we learn the function? We are given a collection of input-output pairs, and we try to learn the function. So when the network is trying to learn to classify, it's going to try, it's basically, suppose you are trying to learn this double pentagon, you'd be given samples of data of this kind, where you have data labeled 1 inside these double pentagons and labeled 0 outside. And from these samples, you have to learn this rather poorly drawn double pentagon decision boundary. If I'm working on 2 inputs, this is what the network has to learn. It has to learn to output a 0 outside the double pentagon and a 1 inside. The problem is you're never going to see such clean decision data, where all the data points inside the double pentagon are clearly labeled 1 and all the points outside are labeled 0. What you're going to see is something a little more fuzzy. You're going to see some blue dots in the red region. You're going to see some red dots in the blue region. And somehow from this mess, you still have to figure out that the desired function is this double pentagon. So, but what do you actually learn, right? So to see this, let's go back and take a look at this single perceptron. Say I want to learn to distinguish, I want to learn this decision boundary, which is just a line. What you would be given are just these dots. Some samples labeled 1 on the one side, some samples labeled 0 on the 0 side. And from just these dots, we have to learn the function. So the way we will do it, if you just had a single perceptron, basically this means that you're given this collection of red and blue dots, and you're told, find me the hyperplane which separates the two. Because now once I know the equation for the hyperplane, then I know the equation for the boundary, I know the equation for the perceptron. And your standard perceptron algorithm, which I won't spend any time on, will capture that for you just fine, in a finite number of steps. The real problem is that you're not going to have such cleanly separated data, right? You're going to have some well, in this case, green dots, blue dots on the red side, red dots on the blue side, and so on. And there's no single line that will clearly separate the two colors. So what exactly is happening over here? Let's take a look at a one-dimensional example to get the best idea. I'm going to use a 1D visualization. So now here the input is just 1D. And the output, the desired output is either 0 or 1. What you will actually get is data of this kind. You're going to have blue dots leaking into the red region, red dots leaking into the blue region, clearly. Now a linear classifier for one-dimensional data is a threshold, and clearly these two classes are not linearly separable. And so if I just give you a neural multilayer perceptron and say learn it, remember an MLP is a universal approximator. There's nothing stopping it from learning this function. This is almost certainly not what you want, but there's absolutely nothing stopping the network from learning this function. Now here's the problem. How do we even know that learning this function is the wrong thing to do? Who gave you that? I mean, you work with vague intuitions and say, this is overfitting. Really? How do you know this is overfitting? How do you know that your real life data doesn't actually follow this kind of function? You really don't. So we are going to use a slightly different intuition to arrive at what we actually do. Let's go to a slightly, let's take an extreme case. Let's say I have this one value of X where I get both red dots and blue dots, right? So if I have just this one, that means that at this point, neither 0 nor 1 is the correct answer, exact correct answer. 0 is going to be wrong for some instances. 1 is going to be wrong for other instances. In this situation, what must I output? Let's say I have 90 instances of 1 over here and 10 instances of 0. And I train my network. What must the output of the network be at this point? Should it be 1 because red dominates? Or should it be 0.9 because 90% of the output of the values at this particular X are red? Now, intuitively and even logically, 0.9 is the reasonable thing to be doing. Why? Because 0.9 gives you enough information to actually get this more quantized function out of it. I could just apply a threshold of 0.5 and say, whenever this number is greater than 0.5, output a 1. And so I would naturally sort of output a 1 every time over here because 0.9 is greater than 0.5. So I'm able to convert this 0.9 to this function, but I can't go back the other way. So this 0.9 is the a posteriori probability of 1 given X. And this is potentially much more useful than a simple 1-0 decision, right? It's also more realistic. But then here's what I do. I don't place them all at exactly the same point. I'm going to jitter them. So I still have 100 points, but no two of them have the exact same X value. Some of them are shifted a little right, some of them are shifted a little left. And so this means that it's technically feasible for me to learn a function of this kind because these points are not exactly at the same spot. They're not overlapping. In this case, should I be learning that wiggly green function or should I still be learning 0.9? What is the answer? And intuitively, again, this is where we really, really slide into intuition, right? Intuitively, the correct thing for us to be learning is to output the value 0.9 because a jitter of 10 raised to minus 17 should not change what the network gives you. It's basically effectively the same thing. And so what we really want is the network to give you an ensemble average, but this must be insensitive to small perturbations. And the moment I begin saying something of this kind, you immediately begin to see the issues that arise. What is a small perturbation? We don't know, right? So so instead, we will let statistics deal with it for us. Consider this. I'm going to allow for small perturbations. So at each point, I'm going to look at a small, at each x, I'm going to look at a small window around that x and plot the average value of the training samples within that window. And as I go left to right, I'm going to see more and more instances of 1, fewer and fewer instances of 0. And so the overall plot is this guy. And this is the function that I'm going to try to learn. Now, the actual function is going to depend on the nature, on the width of this window. I'm not going to hard code it. I'm going to let statistics deal with it for me. But the overall function looks like this. Class 1 becomes increasingly probable going left to right, which is very typical in almost all problems in one dimension, which is why we like the sigmoid activation. The sigmoid activation actually captures just exactly this kind of behavior. So that's the reason output neurons in your network tend to be sigmoids or softmax. A sigmoid perceptron with a single input models the a posteriori probability of a class given the input, or single vector input. I'm not speaking of a scalar. Now, so also when I have a two-dimensional example, I'm going to have blue dots on the red side, red dots on the blue side, no line clearly separates the two. So the function that I'm going to learn is a sigmoid of this kind. This function here, which is what we usually use, ends up being a sigmoid. And what the sigmoid actually gives you is the a posteriori probability of class 1 given the input. Now, this is a curve. This is a folded sheet. So, but this is still a linear classifier. Why am I calling it a linear classifier? Because if I use any kind of threshold on this probability and say, if this probability is greater than 0.4, I'm going to call the output 1. Then I draw the locus of all of the values where this probability is exactly 0.4, that locus will be aligned. So this is a linear classifier. And so basically what this means is that we are going to try to learn a function of this kind, basically a sigmoid, that explains the data, but then we will learn it using a statistical approach. Now, if the probability of 1 given x is given by a sigmoid, I'm going to call the other label -1 for convenience. The probability of -1 is going to be 1 minus the sigmoid, which is just a sigmoid flipped the other way. And as you can see, flipping the so for the probability of 1 is 1 over 1 plus e raised to minus of this affine combination. The probability of -1 given x is 1 over 1 plus e raised to plus of this affine combination. I can write both jointly in a single formula and say the probability of y given x is 1 over 1 plus e raised to minus of y times the affine combination. You can see that when y is 1, the sign simply becomes minus. When y is -1, the sign becomes plus. This is a generic formula for every combination of x and y. And now, if I'm given a collection of training instances, which includes x and y's, then the joint probability of all of my training data, assuming that all of my training instances are independent, is simply going to be the product of the probabilities of the individual training instances, which this joint of pxy, I can decompose it as the probability of x times the probability of y given x. So this entire joint probability of my entire training data is going to be the product over all training instances of the logistic of this sigmoid function computed at each x times p of x. And if I take the log probability of my training data, this p of x term comes out, and all I'm left with is the negative of the log probability. All I'm left with is the log sum over all training instances of the log of the sigmoid, which is minus sum over I log of 1 plus e raised to minus y times the affine combination. Now, where am I getting at to all of this? So if I try to learn my model using maximum likelihood estimation, which is a statistically extremely robust, asymptotically unbiased, and well-motivated technique to learn my model parameters. That is going to give me, say, learn my parameters to maximize the log probability of the training data. But then again, P of X is not a function of the parameters of the model. So you can ignore this first guy. So you're just left with argmax of this log probability of the training data, which ends up giving you a term which ends up being exactly equal to minimizing the KL divergence between the desired output Y and the actual output of the network. So I'm sort of glossing over this really quickly, but the point of this is that our standard training technique when we train classifiers, which is to just minimize the KL divergence between the output of the network and the desired output, as actually a statistically motivated maximum likelihood estimation technique, which naturally sort of imposes draws on the statistical properties of the input, which gives us some very nice behaviors vis-a-vis training, which we like, which is why we like using KL divergence, the cross entropy or KL divergence based training so much. But anyway, assuming you're doing all that, so now you end up with this mixed up data. You're training a nonlinear classifier. The network is trying to learn a function of this kind, and for a sufficient network, the network is trying to learn a function of this kind. Now, suppose you actually had perfectly clean data, where you had red data, the reds only inside the double pentagon and the blues only outside the double pentagon. Then we know that a sufficient network with appropriate parameters, which is shown to the right, can learn this decision boundary perfectly. But then consider this final neuron of this network. That final neuron of the network is a standard perceptron. And we know the standard perceptron is a linear classifier. So if a linear classifier is actually able to give you this perfect decision boundary, then it means that at this point, the inputs that went into the linear classifier were such that the red and the blue data points were perfectly separated. So which means that if you plotted the y1, y2, then the y1, y2 values would give you a plot of the kind that we have to the left, where all the red data points lie clearly on one side of a hyperplane, and all the blue data points lie on the other side of the hyperplane. And only if that happens will this final neuron be able to exactly distinguish between the red and the blue data points. So what this means is that this perfect network that actually learns to model this double pentagon decision boundary actually comprises two components. The lower part of the network is actually a complex machine which takes all of these inputs and moves all the data around such that they are now linearly separable. And the output is simply a linear classifier that operates on this linearly separable data. In fact, you don't even need a perceptron at that point. You can attach any linear classifier. For example, an SVM on top, right? Or an SVM with slack. Now, the point of this is that this lower guy is basically learning to obtain linearly separable features from the input. The upper guy simply captures your standard logistic, so your standard sigmoid on those features. And so a classification MLP comprises two components: the feature extraction network that converts the input into linearly separable features, and the final classifier that operates on the separable features. And I'm missing some slides over here. So I think I did a bad job of editing it. My point over here is that even now, if you go back and apply the same logic to this inseparable case, There too, what the network will eventually give you is it gives you the a posteriori probability of the red class at each point, and the network ends up being a combination of two units, the lower feature extraction unit that makes it easy for you to compute the a posteriori probabilities using a sigmoid, and then the sigmoid itself, which captures the a posteriori probabilities. Now, as it turns out, the time is 3:25. I don't think I will have time to go through much else, but let me just spend the last few minutes. So how exactly do these lower layers, so we found that all of these guys, right up to here, the network learns to learn linearly separable features from the input. But what if I go below the penultimate layer? What about these guys? What do these guys learn? Now, that hasn't been very well understood yet, but the most reasonable hypothesis, which empirically seems to hold, is what I call the manifold hypothesis, is that the data, the classes are linearly separable or almost linearly separable by the time you get to this Y layer. And so what each of these layers does is that as the data passes through the network, at each layer, the classes become increasingly linearly separable. And to show you how this happens, here is a synthetic example. I don't know if this will, oh my video is kind of not working. So this should have been working. So I have a broken video. Here we have drawn data from these circular decision boundaries, right? And if the video had worked, this is a very simple 3-layer network. There's there's actually it's a 1 hidden layer network, 2-dimensional input, three neuron hidden layer, and finally the output layer. And what I wanted to show you was that as you train the network, this decision boundary, which is basically a circle, when you take it into the 3-dimensional hidden layer space, first it gets put in 3 dimensions like a sheet over here. Then it gets warped so that instead of just being a 2-dimensional sheet, it actually gets stretched out and now fills out the 3-dimensional space. And then in the 3-dimensional space, when you actually look at the projections, you actually end up with, or you end up finding yourself in a situation where you can draw a slicing plane where all the red points fall below the plane and the blue points fall above it, and therefore you're actually able to learn the decision boundary. It kind of fizzled out because I'm not sure why entirely these figures are gone. Anyway, I'm going to stop right here, folks. All the information that I wanted to convey during this lecture are on the slides. So with due apologies, I'm going to stop, and I'll take maybe a couple of more questions if you have any. And then I have to drop out at 3:30 if you don't mind. Questions, anyone?
Thank you, Bhiksha. I don't see any questions in the Q&A yet.
Nick has his hand raised, actually. So let me...
It's late over there. It's 8:30. I mean, people will be tired. It's more tiring to listen to than to say.
Can you give Nick permission to speak?
Yes, hello. Thank you for a super interesting lecture. I'm wondering about time series. We obviously have a session on that tomorrow, but can you comment about MLP's ability to model time series without going down the RNN route?
So again, pretty much all of the ideas, you can always think of time series. Now, abstractions are a problem, but we like to work with abstractions. You can think of time series as data in a very high dimensional space. And so pretty much all of the intuitions that I have been trying to convey over here translate directly to time series. Time series are not special data. The data are not special. Our models exploit structure and the data in order to be much more compact, just like convolutional models exploit repeating structure and the data to give you more compact models. So also time series models exploit structure and the data to give you more compact models. But other than that, it's always useful to think of these as very high dimensional data, and all of these concepts still apply.
Thank you.
Great. Any more questions?
All right.
Okay, Bhiksha, so you have to leave soon, right?
I have to leave in 2 or 3 minutes, but
okay, if somebody has another question, but
no, I can take a couple of questions. I have a meeting at 3:45 or so, I'll just, if you let me run, I'll go through to 3:45 or 4. So I gave myself a hard cutoff at 3:30. That's all.
That's great. So is there any further question here?
Can I make one comment?
Yeah.
So your initial comment about myelination, I think the case is actually even stronger than you propose, because in computational biology, there's clear evidence to suggest differential expression of the gene that drives the expression levels of myelin that actually also leads to higher levels of electric conductivity in the brain, thus suggesting high degrees of specialization.
Really? Yeah. Huh. So do you have any citations, any papers you could point me to?
None other than the one I shared with you last year.
Same thing? All right. Okay. Oh, yes, I do remember. Yeah. So I actually cite that in one of my lectures, that particular one. Yeah.
Thanks.
All right, folks. Thank you.
Okay. Thank you very much.
There's a couple of questions.
And Nick, I don't know how you have the patience to come back and listen to these things every year, but thank you.
Yeah,
I'm a slow learner.
There are some questions now in the Q&A.
Oh.
That's
So there is one about, is there any book on systematic introduction to neural networks?
What do you mean systematic interactions?
I don't know. Can they specify? Is it neural networks 101 or?
Like with very much detail, I think it's implied. Like very, very slowly, right?
Yeah. There are many, many books of this kind, but they are not recent. You have to be at least as old as me to know that these things exist. Rumelhart, Hinton and Jacobs, Rumelhart, Jacobs, and you have to go back to Rumelhart's book, the yellow book and the brown book and the blue book from the late 80s, early 90s. They actually work your way up. They are so old that CNNs were not around when those books were written. But they really teach you this stuff.
Okay.
Yeah. Is there any further question? If not, I think the speaker has to. Bhiksha has to tell another.
No, but I can take the question.
Okay, good.
Yeah. No, so there is a question about if they can contact you by email or Slack to follow up.
Sure. I mean, email Bhiksha at CS. It's there, right?
Yeah. So also in the Slack, you will be available in the next days to answer more questions.
Absolutely.
Okay.
Then the other question is, Mohan says, I have a general question. This may be more about RL. Can machines or neural networks be programmed to intentionally make mistakes? If yes, is dumbness a subset of intelligence?
You're asking the wrong person. It's a very deeply philosophical question as far as I can tell. I'm assuming that you can always add noise. So, adding noise you can always program a network to make mistakes. And we do that all the time, right? I mean, anytime you do exploration versus exploitation, it's not intentionally making mistakes, but intentionally, potentially making mistakes. We do that all the time. And we try to learn from these mistakes. That's what RL really does. But that's what all machine learning really does, learning from mistakes to some extent. If our systems were completely deterministic and never explored, they'd never actually learn anything.
Nice. So I think that's all the questions. I think there was one, but just disappeared. So I think that those are all the questions.
Thank you for this was
Thank
fun.
you very much. Thank you very much, Bhiksha.
Yeah.
Thanks a lot, Bhiksha.
Yeah, thank you.
And I'll be on Slack if the students want to talk to me, right?
Okay, great.
Bye.
Bye.
Thank you.
Bye.
Bye.
Okay, see you guys tomorrow at 9 o'clock.
See you. Bye.
Yeah. See you, everyone.